Before the first star ever burned, before the first atom ever cooled, before time had learned how to count itself, the entire universe was smaller than a single atom, compressed, silent, waiting. Everything you have ever known, every ocean, every mountain, every breath you have taken, was once folded into a space so small it defies imagination. And tonight, we are going to unfold it. By the time we reach Fact 200, the sky above you will feel different. Not louder, not brighter, but deeper. So let your breathing slow. Let the day soften and fall away. You are about to drift through 200 true things about the universe, and somewhere along the way, you may begin to feel just how extraordinary it is that you are here at all. Close your eyes and try to hold that number for a moment. 4.54 billion years. It is a number so large it has no real shape in the human mind, and perhaps that is all right. Perhaps some things are meant to be felt rather than counted. This planet beneath you, the one holding you so steadily right now, was not always here. It gathered itself slowly, patiently, from a vast spinning cloud of ancient material, dust and gas and ice drawing together over millions of years, pulled by nothing more than gravity and time. Grain by grain, rock by rock, until there was something solid, until there was something that could one day hold oceans and mountains and you. Right now, without any sensation of movement whatsoever, you are hurtling through space at 67,000 miles per hour. Your body feels nothing. The air around you feels nothing. The ground beneath you gives no tremor, no hint of the extraordinary velocity at which it is carrying you through the darkness. There is something deeply settling about this, the idea that stillness and motion are not opposites but companions, that you can be moving faster than almost anything on Earth and still feel in every cell of your body completely and utterly at rest. You are at rest right now, and you are also flying. Our planet does not stand straight. It leans, ever so slightly, at an angle of 23.5 degrees, a gentle, permanent tilt that it has carried for billions of years. And because of that lean, different parts of the Earth receive different amounts of sunlight at different times of year, giving us the slow turning of the seasons. The warmth of summer arriving like a long exhale, the quiet withdrawal of autumn, the deep stillness of winter, when the world grows dark early and the nights stretch long and soft. All of it, every season you have ever felt, every first cold morning and every warm afternoon, is a gift of that one small, ancient tilt. The moon is leaving us, though it is doing so with extraordinary patience. Every year, it moves about 1.5 inches further away from Earth, pulled gradually outward by the same gravitational forces that cause our ocean tides. 1.5 inches sounds like nothing, and in a human lifetime, it is almost nothing. But over millions of years, that quiet drift adds up. The moon was once much closer, hanging larger and more luminous in the ancient sky above a world that had no eyes yet to admire it. It is moving away slowly, the way all things eventually move, gently and without announcement, into a greater distance. Among all the moons orbiting all the planets in our solar system, and there are many, more than 200 confirmed so far, ours ranks 5th in size. It sits in quiet company with Ganymede and Titan and Callisto and Io, each of them vast and strange and worlds in their own right. But there is something particular about our moon, something that sets it apart from the others. It is unusually large relative to the planet it orbits, so large that some astronomers describe the Earth and Moon not as a planet and its satellite, but as a double world. Two bodies moving together through space in a slow, ancient, gravitational embrace. Space begins closer than most people imagine, just 62 miles above your head, a distance you could drive in an hour on an open highway. The atmosphere thins to almost nothing and the sky gives way to the deep black of space. That boundary is called the Kármán line, a quiet threshold between the world we know and everything beyond it. But Earth does not end there entirely. A faint, almost ghostly layer of hydrogen atoms called the geocorona extends far beyond the Kármán line, drifting outward past the moon itself, nearly 390,000 miles into space. We are, in a sense, larger than we appear. Earth breathes further into the darkness than the eye can see. The distance between Earth and its moon is about 239,000 miles, and within that stretch of space, that single gap between our world and its quiet companion, you could line up every other planet in the solar system and they would all fit with a little room to breathe. Mercury and Venus, Mars and Jupiter and Saturn, Uranus and Neptune, those cold blue giants at the edges of everything, all of them side by side nestled into the space between here and the moon. It is a reminder that the solar system, for all its grandeur, is mostly made of distance, mostly made of the beautiful, patient emptiness between things. Fire is rarer than we think. Across the entire known universe, across billions of galaxies and trillions of planets and all the extraordinary variety of worlds that exist out there in the dark, Earth is the only place we know of where a flame can naturally exist. Fire needs oxygen, and our atmosphere provides it in exactly the right abundance. Somewhere out there, other worlds have their own forms of burning, their own chemical reactions releasing light and heat into alien skies. But a campfire, a candle flame, a spark catching in dry grass on a summer evening, that is ours alone. Something that belongs, quietly and specifically, to this world. Every year, Earth traces an enormous ellipse around the Sun, a journey of roughly 584 million miles completed with quiet, unwavering regularity. Which means that in the years since you were born, this planet has carried you more than 575 million miles through space, possibly much further depending on your age. You have been a traveler your entire life, moving through the universe on a scale that staggers the imagination, and you have felt none of it. Every birthday you have celebrated was actually an anniversary. The Earth returning after its long annual journey to roughly the same place in its orbit where you first arrived. We do not live at the center of our galaxy. We live in the quieter outskirts, in a gentle region of one of the Milky Way's spiral arms, about 26,000 light-years from the luminous, churning core. The galactic center is a crowded and violent place, dense with stars, threaded with magnetic fields, anchored by a supermassive black hole of immense proportions. Out here, where we are, things are calmer. The stars are more spread out, the nights are quieter. We are, in a sense, residents of the galactic suburbs, far enough from the chaos at the center to have evolved over billions of years in relative peace. On top of Earth's orbit around the Sun, our entire solar system is also moving, sweeping around the center of the Milky Way at roughly 514,000 miles per hour. The Sun, the planets, the moons, the asteroids, the comets, everything, all of it carried together in a vast, slow arc through the galaxy. And yet there is no sensation of this motion, no wind, no vibration, no sense of the extraordinary speed at which your entire cosmic neighborhood is traveling through space. The universe is very good at moving things gently, at carrying them forward without disturbing their rest. One full trip around the Milky Way takes our solar system approximately 230 million years. Astronomers call this a cosmic year or a galactic year, a unit of time so vast it makes human history feel like the briefest of moments. In one cosmic year, entire mountain ranges rise and erode, species appear, flourish and vanish, oceans shift, continents rearrange themselves. Our solar system has completed this enormous orbit roughly 20 times since it first formed, each revolution a slow, silent journey through different regions of the galaxy, through different densities of stars and dust and ancient light. One galactic year ago, the last time our solar system occupied this same position in its orbit around the Milky Way, Earth was a very different world. The greatest mass extinction in our planet's history, the Great Dying, had only just ended. Nearly 96% of all marine species and 70% of land vertebrates had vanished. And from that devastated, slowly recovering world, the first dinosaurs were beginning to emerge, small and tentative at first, feeling their way into a changed planet. They could not have known, of course, that by the time the solar system returned to this position, they would be long gone, replaced by something that would one day look up and wonder where it came from. Our address in the galaxy is more specific than simply the Milky Way. We live in a smaller partial spiral arm called the Orion Spur, sometimes called the Orion Arm, a modest offshoot nestled between two of the galaxy's larger, more prominent arms. It is a quieter neighborhood, as galactic neighborhoods go, not as densely packed with stars as the inner arms, not as sparse and cold as the outer edges. The Orion Spur is an in-between place, a gentle middle ground, and perhaps it is not a coincidence that life found its footing here, in this unhurried, neither too crowded nor too empty corner of an ancient spiral galaxy. On either side of us, curving through the galaxy in long luminous arcs, lie two of the Milky Way's major spiral arms, the Sagittarius arm, closer to the galactic center, and the Perseus arm, reaching further out towards the edges. We live between them in the quieter space where the star density is lower and the cosmic environment is gentler. This position may be one of the reasons life was able to develop here. The major spiral arms are regions of higher radiation, denser gas, and more frequent stellar activity. Out here, between the arms, there is room to breathe, room to grow slowly, over billions of years, into something as delicate and intricate as life. Between 100 and 400 billion stars, the range itself is a kind of poetry. We cannot count them precisely enough to narrow it further, which means the galaxy holds more stars than our best instruments can yet fully resolve. Each of those stars is a sun. Many of them are larger than ours. Many of them are older. Most of them, we now believe, have planets. Worlds circling in the dark around ancient fires, some perhaps warm and wet and patient, waiting in their own quiet orbits for something to look up and notice the sky. 100 to 400 billion suns, and ours is just one of them, burning gently in the outskirts, warming one small blue world. For decades, textbooks told us the Milky Way was about 100,000 light-years across. Then the Gaia space mission, a remarkable observatory that has been carefully mapping the positions and motions of billions of stars, began sending back data that told a different story. Our galaxy, it turns out, is considerably larger than we thought. Its disk stretches somewhere between 170,000 and 200,000 light-years from edge to edge, a vast, slowly rotating structure of ancient light and gas and dark matter that we are only beginning to understand in its true proportions. The universe has a way of being larger than we expect. It has always been larger than we expect. Our galaxy does not travel alone. It is part of a small family of galaxies called the Local Group, a gravitationally bound collection of more than 54 galaxies spread across a region of space roughly 10 million light-years wide. The Local Group is dominated by two large spiral galaxies, our own Milky Way and the Great Andromeda Galaxy, with dozens of smaller dwarf galaxies orbiting around them like quiet satellites. There is something deeply comforting about this. The idea that even on the scale of galaxies there is belonging. There are neighbors. There are things that hold together, drawn by invisible forces into a shared and lasting proximity. More than 54 galaxies share the gravitational neighborhood we call home. Some of them are large and spiraling and full of hundreds of billions of stars. Others are small and faint, dwarf galaxies containing only a few million stars, drifting in the outer reaches of the group like dim lanterns at the edges of a gathering. The Magellanic Clouds, visible from Earth's southern hemisphere as faint smudges of light in the night sky, are two of our nearest galactic companions, small, irregular galaxies being slowly drawn into the Milky Way's gravitational embrace. They have been traveling alongside us for billions of years, luminous and patient, companions on the long journey through the universe. Look up on a clear, dark night in the northern hemisphere, and with patient eyes you can find a faint, soft smudge of light in the constellation of Andromeda. That smudge is an entire galaxy, 2.5 million light-years away, containing perhaps 1 trillion stars, the most distant object visible to the naked human eye. The light reaching your eyes from Andromeda tonight left its source 2.5 million years ago, when our ancestors were still learning to shape stone tools on the African savanna. That ancient light has been crossing the universe ever since, patient and unhurried, arriving at last at the quiet darkness behind your eyes. Right now, without any fanfare, the Andromeda Galaxy is approaching us. Drawn together by the gravity of their combined mass, the Milky Way and Andromeda are moving toward each other at roughly 70 miles per second. It sounds fast, and in human terms it is, but on galactic scales, it is a slow and stately approach, a motion that has been building for billions of years, and will continue for billions more before anything dramatic occurs. There is no urgency to it, no collision imminent in any time frame that touches human experience. Just two great spirals drifting toward each other across the dark, following the oldest and most patient of all forces. In approximately 4.5 billion years, the Milky Way and Andromeda will meet. The word collision perhaps conjures images of destruction, of catastrophe, of two things shattering against each other. But a galactic collision is something far stranger and more beautiful than that. Because galaxies are mostly empty space, the stars within them will pass by one another like ghosts, drawn into new orbits by the shifting gravitational landscape, swept into streams and arcs and entirely new configurations. The spiral arms will distort and flow. New stars will be born from the compressed gas clouds. And over hundreds of millions of years, something new will slowly take shape from the intermingling of two ancient galaxies. The galaxy that will eventually emerge from the merging of the Milky Way and Andromeda has been given an informal name, Milkomeda. It will likely be an elliptical galaxy, smooth and rounded, no longer carrying the graceful spiral arms of either of its parent galaxies. The Sun, if it still exists by then, may find itself in an entirely different region of this new structure, surrounded by stars that were once part of a galaxy 2.5 million light-years away. There is something quietly profound about this. The idea that what we call home is not a permanent shape, but a temporary arrangement, beautiful and intricate and slowly moving toward a transformation we will never see. Beyond the local group, the scale expands again. Our small family of galaxies is itself part of a much larger structure, the Virgo supercluster, a vast collection of galaxy groups and clusters spanning roughly 110 million light-years. At its heart lies the Virgo cluster, a dense congregation of more than 1,000 galaxies whose combined gravity gently influences the motion of everything around it, including our own local group. We are, in a sense, falling slowly toward the Virgo cluster, drawn by its enormous gravitational pull at a pace so gradual it registers only over billions of years. Even superclusters have centers of gravity. Even the largest structures lean towards something. The Virgo supercluster holds at least 100 galaxy groups and clusters within its vast gravitational embrace. Each of those groups contains dozens of galaxies. Each of those galaxies contains billions of stars. Each of those stars may have worlds circling it in the dark. The numbers spiral outward into a kind of comfortable incomprehensibility, not frightening, but softening. The way very large numbers eventually stop feeling like quantities and start feeling like weather. Like something you simply exist inside of, without needing to count it. You are inside the Virgo supercluster right now in one of its 100 groups, on one of its billions of worlds, breathing quietly at the end of a long day. Everything in our solar system, every planet, every moon, every asteroid and comet and drifting grain of ancient dust, accounts for just 0.14% of the total mass. The Sun holds the rest. All of it gathered into one enormous luminous sphere of plasma, burning at its center with a quiet ferocity that has not dimmed in 4.6 billion years. Jupiter, the largest planet, contains more mass than all the other planets combined, and yet even Jupiter is a small thing against the Sun's immensity. Our solar system is, in the most literal sense, almost entirely made of star. The planets are footnotes, beautiful, intricate, extraordinary footnotes, but footnotes nonetheless. The Sun is not young, but it is not old either. At 4.6 billion years, it sits comfortably in the middle portion of its expected lifespan, a yellow dwarf star burning steadily through its hydrogen fuel at a pace that astronomers expect to continue for another 5 billion years or so. In stellar terms, it is in its prime, stable and reliable, neither swelling toward the end of its life nor still finding its footing in early formation. There is something reassuring about this, that our star, the one warming your face on sunny afternoons and painting the sky at dusk, is a steady, unhurried, middle-aged thing with billions of years yet ahead of it. Every second, without pause, without variation, the Sun's core fuses 600 million tons of hydrogen into helium through a process called nuclear fusion. 600 million tons every second, released as light and heat and solar wind that flows outward through the solar system, warming planets and illuminating moons and eventually fading into the cold darkness between the stars. This has been happening for 4.6 billion years. It will continue happening for billions more. The sun is the most constant thing in our world, rising and setting with such reliability that we have built our entire sense of time around it. And yet, at its heart, it is a place of almost incomprehensible, ceaseless transformation. The light touching your skin on a warm afternoon left the surface of the sun 8 minutes and 20 seconds before it arrived. In that brief window of time, it crossed 93 million miles of empty space, traveling at 186,282 miles per second until it found its way through Earth's atmosphere and landed gently and without effort on you. In a very real sense, you never see the sun as it is right now, only as it was 8 minutes ago. The sun you know is always slightly in the past, a memory of light arriving just behind the moment that created it, faithful and warm and only ever a few minutes late. At the very center of the sun, where the pressure of 333,000 Earth masses of material pressing inward from all directions creates conditions unlike anything on the surface of any planet, the temperature reaches 27 million degrees Fahrenheit. At that temperature, hydrogen nuclei move fast enough to overcome their natural electromagnetic repulsion and fuse together, releasing the energy that has powered our solar system since before Earth existed. The surface of the sun, by comparison, is a relatively mild 10,000 degrees Fahrenheit, still incomprehensibly hot by any human measure, but cool enough that the sun's outer layers appear almost gentle against the raging furnace buried within. There is no comfortable human analogy for the sun's energy output. Every second, it releases approximately 100 billion megatons of energy, a number that passes through the mind without quite finding purchase, too large to feel, too immense to picture. The most powerful nuclear weapon ever detonated by human hands released about 50 megatons of energy in a single moment. The sun releases 2 billion times that amount every second, continuously, without variation, without rest, as naturally and effortlessly as breathing. It has been doing this for 4.6 billion years. The warmth on your face on a summer morning is a whisper of something almost beyond imagination. Every second, through the process of converting hydrogen into helium, the sun loses approximately 4 million tons of mass, transformed directly into energy through Einstein's famous equation, E equals mc squared. 4 million tons per second, disappearing into light and heat and the solar wind that fills the space between the planets. And yet the sun is so inconceivably massive that this loss is trivial against its total bulk. In its entire 4.6 billion year lifetime, the sun has lost less than 0.1% of its original mass to fusion. It is a fire so large that burning for billions of years has barely made a dent in the fuel available to it. The sun is not running out of fuel in any time frame that touches human experience, or even the experience of life on Earth as we know it. It has enough hydrogen remaining in its core to continue fusing for approximately another 5 billion years, burning as steadily and warmly as it does today. What happens after that is a different story. The sun will swell into a red giant, its outer layers expanding outward past the inner planets. But that transformation is so far in the future that it sits beyond the edge of all meaningful imagination. For now, and for all of human history to come, the sun will rise every morning and set every evening reliable and warm and ancient. The sun does not simply radiate light into space, it also exhales, continuously streaming a flow of charged particles called the solar wind outward in all directions at roughly 1 million miles per hour. This wind fills the entire solar system, pushing against the atmospheres of planets, sculpting the tails of comets so they always point away from the sun regardless of the direction of travel, and eventually fading into the interstellar medium far beyond the outer planets. On Earth, the solar wind interacts with our magnetic field to create the aurora borealis, those luminous, shifting curtains of green and violet light that appear near the poles on clear nights, the visible breath of our nearest star painting the sky. Mercury moves through space with a kind of urgent efficiency, completing its entire orbit around the Sun in just 88 Earth days. It is the innermost planet, racing along a tight elliptical path close to the Sun's enormous gravitational pull, and its speed is a direct consequence of that proximity. The closer an object orbits a star, the faster it must move to maintain its orbit. A year on Mercury passes in less than 3 of our months, and yet a day on Mercury, one full rotation on its axis, lasts nearly 59 Earth days, which means the sun rises and sets with extraordinary slowness on its scorched and cratered surface, tracing a long, brilliant arc across an airless black sky. Venus is a world of beautiful contradictions. It rotates on its axis so slowly and in the opposite direction to most planets that one full rotation takes 243 Earth days. And yet its year, the time it takes to complete one orbit around the Sun, is only 225 Earth days. This makes Venus one of the only places in the solar system where a day is technically longer than a year, in one sense of the word. But the interaction between its slow rotation and its orbital motion means that sunrise to sunrise, a solar day, takes only about 117 Earth days. On Venus, the sun rises in the west and sets in the east, moving slowly across a thick, cloud-covered sky the color of old brass. On the surface of Mars, rising from the rust-colored plains with extraordinary patience, stands the largest volcano in the entire solar system. Olympus Mons is 16 miles tall, nearly 3 times the height of Mount Everest, and so wide at its base that if you stood at its center, the edges would lie beyond the horizon. You could not see from any single vantage point that you were standing on a volcano at all. It is believed to have formed over billions of years as the Martian crust, which unlike Earth's does not move in tectonic plates, remained stationary above a single volcanic hotspot, allowing lava to pile up slowly and patiently into something almost incomprehensible in scale. Jupiter is not simply the largest planet in our solar system, it is in a category of its own. So large that every other planet, from tiny Mercury to distant Neptune, could fit inside its volume simultaneously, with room remaining. Its diameter is 11 times that of Earth. Its mass is more than twice that of all the other planets combined. It is a world made almost entirely of hydrogen and helium, a swirling banded giant with no solid surface to stand on, no shoreline, no ground. Just atmosphere deepening into denser atmosphere until, somewhere near the center, pressure transforms hydrogen into a liquid metal that conducts electricity and generates the most powerful magnetic field of any planet in the solar system. In the southern hemisphere of Jupiter, there is a storm. It has been there for at least 350 years, first observed by astronomers in the 17th century, spinning in a persistent high-pressure system that has outlasted every human civilization that has risen and fallen in that time. The Great Red Spot is an anticyclone, a storm rotating in the opposite direction to those in Jupiter's northern hemisphere, its winds reaching speeds of about 400 miles per hour at its outer edges. It is not fully understood why it has persisted for so long, or what gives it its distinctive reddish color. It is simply there, as it has always been, turning slowly and enormously in the cloud tops of the largest planet in our solar system. To understand the scale of Jupiter's Great Red Spot, consider this. It is large enough that 3 planets the size of Earth could be placed inside it, side by side. 3 entire worlds, each one home to mountains and oceans and all the extraordinary complexity of a living planet tucked into a single storm on a gas giant. The Great Red Spot has actually been shrinking over the past century. It was once estimated to be large enough to hold 6 or 7 Earths, and scientists are still working to understand what is driving that slow contraction. Even at its current reduced size, it remains one of the most dramatic and enduring weather systems in the solar system, a quiet, turning enormity in the clouds of Jupiter. Saturn's rings are one of the most beautiful structures in the solar system, and they are made of something surprisingly simple: billions upon billions of individual pieces of ice and rock, ranging from tiny grains to house-sized chunks, each one orbiting Saturn independently in a flat, gleaming disk. From a distance, they look solid, like a smooth surface one could walk upon. But they are not solid at all. They are a vast, dynamic collection of individual particles, each following its own orbital path, occasionally colliding gently with its neighbors, the whole system maintained by a delicate balance of gravity and motion that has persisted for hundreds of millions of years. Within Saturn's rings, the range of sizes is extraordinary. Some particles are no larger than the grains of sand between your fingers at a beach, small enough to drift and swirl in the subtle gravitational currents between the ring bands. Others are enormous, the size of houses or buildings or mountains, tumbling slowly through space in long, silent orbits. Most of the material is water ice, which gives the rings their bright, reflective quality. They catch sunlight and return it with a luminous efficiency that makes Saturn, even through a modest telescope from Earth, look almost too beautiful to be real, like something placed there deliberately for the pleasure of the looking. For all their width, Saturn's rings extend outward nearly 175,000 miles from the planet's equator. They are astonishingly thin. In some regions, the rings are only about 30 feet thick. 30 feet, the height of a 3-story building. If you were to scale Saturn down to the size of a basketball, its rings would be thinner than a sheet of paper. This extraordinary flatness is a consequence of the physics of orbital mechanics. The particles have, over time, settled into a single plane, their vertical motions dampened by countless gentle collisions until the entire vast structure lies as flat and thin as a whisper, wide as a world, thin as a breath. Every planet in the solar system has a tilt, an angle between its rotational axis and the plane of its orbit. Earth's tilt of 23.5 degrees gives us our seasons, but Uranus is tilted at 98 degrees, which means it essentially rotates on its side, rolling around the Sun like a slow-spinning ball rather than a spinning top. The result is a planetary experience unlike any other in the solar system. Each pole of Uranus experiences about 42 years of continuous sunlight followed by 42 years of complete darkness. The cause of this extreme tilt is believed to be a collision with an Earth-sized object billions of years ago, a single ancient impact that permanently changed the orientation of an entire world. Neptune is the windiest place in the solar system. Despite being the farthest major planet from the Sun, receiving only a fraction of the solar energy that drives weather on the inner planets, Neptune generates winds that reach speeds of up to 1,200 miles per hour, faster than the speed of sound on Earth. The source of this extraordinary wind energy is not fully understood. Neptune radiates more heat than it receives from the Sun, suggesting an internal heat source deep within the planet that drives the violent atmospheric circulation at its surface. It is a cold, dark, distant world, and yet it is also one of the most dynamically violent, a reminder that stillness and distance do not always go together. Beyond the familiar 8 planets, our solar system also contains 5 officially recognized dwarf planets: Pluto, Eris, Haumea, Makemake, and Ceres. Each of them is a world in its own right, with its own geology, its own history, its own quiet complexity. Pluto, the most famous of them, was reclassified from planet to dwarf planet in 2006, a decision that caused considerable debate and more than a little affection for the small, cold, heart-shaped world at the edge of the solar system. The New Horizons spacecraft flew past Pluto in 2015, revealing a world of mountains and glaciers and nitrogen plains, far more varied and beautiful than anyone had imagined. Between the orbits of Mars and Jupiter lies a broad region of space populated by millions of rocky and metallic objects, the asteroid belt. These are not the remnants of a destroyed planet, as was once thought, but rather material that never coalesced into a planet in the first place, prevented from doing so by Jupiter's powerful gravitational influence. The total mass of the entire asteroid belt is less than 4% of the mass of the Moon, spread across millions of objects over an enormous region of space. Despite their reputation in science fiction, the asteroids are not tightly packed. The average distance between them is hundreds of thousands of miles. Space between them is vast, quiet, and mostly empty. Comets are time capsules. Composed of ice, dust, and organic compounds, they formed at the same time as the rest of the solar system 4.6 billion years ago, and many of them have changed very little since. When a comet falls inward from the cold outer solar system and approaches the Sun, its ices begin to vaporize, releasing gases and dust that form the glowing coma and spectacular tail visible from Earth. That tail always points away from the Sun, shaped by the solar wind into a luminous stream millions of miles long. For a few weeks or months, a comet blazes across the inner solar system, an ancient, unchanged thing, briefly made brilliant by the warmth of our star. Beyond the orbit of Neptune, in the cold outer reaches of the solar system, lies the Kuiper belt, a broad region of space populated by hundreds of thousands of icy bodies, remnants from the solar system's formation that have remained largely frozen and unchanged for billions of years. Pluto is the most famous resident of the Kuiper Belt. The Kuiper Belt extends from about 30 to 50 astronomical units from the Sun, 1 astronomical unit being the distance from Earth to the Sun, and contains enough material to keep astronomers busy for generations. New objects are still being discovered there regularly, each one a small, cold, ancient world that has been quietly orbiting in the dark since before Earth had continents. Far beyond the Kuiper Belt, at distances almost too large to comfortably imagine, lies the Oort cloud, a vast spherical shell of icy objects that surrounds the entire solar system like a distant halo. The Oort cloud begins roughly 2,000 astronomical units from the Sun and may extend as far as 100,000 astronomical units, nearly a quarter of the way to the nearest star. It is believed to contain trillions of icy bodies, the source of many long-period comets that occasionally fall inward toward the Sun on journeys lasting thousands of years. No spacecraft has ever reached the Oort cloud. It exists at the very edge of the Sun's gravitational influence, the outermost boundary of our solar neighborhood, where the solar system quietly ends and the interstellar dark begins. Before there is a star, there is a cloud, a vast, slow, drifting cloud of hydrogen and helium and fine cosmic dust spread across light years of space, cold and dark and seemingly inert. These clouds are called nebulae, and they are among the most beautiful structures in the universe. Great pillars and curtains and billowing formations of gas lit from within by the young stars they are in the process of creating. A slight disturbance is all it takes to begin the process. A nearby supernova, a passing gravitational wave, a gentle compression from the rotation of the galaxy. The cloud begins to collapse under its own gravity, slowly at first, then faster, drawing inward toward a center of increasing heat and pressure until something ignites. Until a star is born. Our nearest stellar neighbor is a small dim red star called Proxima Centauri, sitting 4.24 light-years away, about 25 trillion miles. It is part of a triple star system called Alpha Centauri, and it earned its name from the Latin word for nearest. Despite being our closest neighbor in the vast darkness between stars, Proxima Centauri is so far away that the fastest spacecraft ever launched by humanity would take tens of thousands of years to reach it. The distances between stars are not empty in a frightening way. They are empty in a quiet way, a reminder of how much of the universe is simply space, patient and dark and immeasurably deep, holding its stars at arm's length from one another. Proxima Centauri belongs to the most abundant class of stars in the universe, the red dwarfs. Small, cool and dim by stellar standards, red dwarfs make up roughly 70% of all the stars in the Milky Way, yet not a single one is visible to the naked eye from Earth, so faint are they against the darkness. They burn their fuel with extraordinary frugality, glowing a deep reddish orange at temperatures far lower than our suns. They are modest, quiet stars, nothing like the brilliant giants that dominate the night sky, and yet they are everywhere. The universe is overwhelmingly populated by these small, patient, slow-burning fires, each one potentially warming its own system of orbiting worlds in the dark. Our Sun will live for about 10 billion years in total. A red dwarf star, by contrast, can burn for trillions of years. Some estimates suggest the smallest red dwarfs could shine for as long as 10 trillion years, nearly 1,000 times the current age of the universe. The universe itself is not yet old enough for any red dwarf to have died of old age. Every red dwarf that has ever formed is still burning. They are the most enduring lights in the cosmos, so slow and steady in their consumption of fuel that they will still be glowing long after every star like our Sun has swelled, expanded and faded into a quiet white dwarf. They are the last fires the universe will know. On a clear night, the brightest star in the sky, blazing blue-white and unwavering in the constellation Canis Major, is Sirius. It is not the largest star nor the most luminous in absolute terms, but its relative proximity to Earth, just 8.6 light-years away, makes it appear brilliant above all others. Ancient civilizations knew Sirius well. The Egyptians oriented temples toward it and used its annual reappearance on the horizon to predict the flooding of the Nile. The Greeks called it the dog star and believed its rising in summer contributed to the heat of those months, giving us the phrase the dog days of summer. That same star, that same blue-white light is still there every winter evening, burning with the same quiet intensity it has always had. What appears to the naked eye as a single brilliant point of light is actually two stars. Sirius A, the bright star we see, is about twice the mass of our Sun and 25 times more luminous. Sirius B, its companion, is a white dwarf, the dense, cooling remnant of a star that was once far larger than Sirius A, but exhausted its fuel long ago and collapsed into a sphere roughly the size of Earth. The two stars orbit each other once every 50 years, locked in a gravitational partnership that has persisted for hundreds of millions of years. From Earth, we see only the brilliance of Sirius A, but it has never traveled through the galaxy alone. In the upper left corner of the constellation Orion, the great hunter standing in the winter sky, there is a star that glows with a distinctly reddish hue. That star is Betelgeuse, one of the largest stars visible to the naked eye, a red supergiant so immense that it defies easy comparison. It is roughly 700 times the diameter of our Sun, though its outer layers pulse and shift, making its exact size difficult to pin down. It is not a stable, orderly star like the Sun. It is a roiling, expanding, brilliantly unstable giant in the late stages of its life, a star that has already burned through most of its fuel and is moving on cosmic timescales toward its end. To understand the scale of Betelgeuse, imagine removing our Sun from the center of the solar system and placing Betelgeuse there instead. Its visible surface, the outer edge of its enormous pulsating atmosphere, would extend past Mercury, past Venus, past Earth, past Mars, all the way out beyond the asteroid belt and past Jupiter's orbit. Earth would not simply be engulfed, it would be deep inside the star, buried beneath hundreds of millions of miles of stellar material. Jupiter itself, that enormous gas giant we think of as vast, would be swallowed whole. And yet Betelgeuse, for all its size, is not even close to the largest star known. It is simply the one close enough for us to appreciate. Betelgeuse is dying, not quickly by human standards. The phrase sometime in the next 100,000 years covers a span of time longer than all of recorded human history multiplied many times over. But on astronomical timescales, it is imminent. The star has already burned through its hydrogen and helium and is now fusing heavier elements in its core, moving through the final stages of stellar evolution with increasing speed. When it finally exhausts its fuel entirely, the core will collapse in a fraction of a second and the outer layers will rebound outward in one of the most powerful events the universe produces, a supernova explosion visible across thousands of light-years of space. When Betelgeuse explodes, the light from that explosion will reach Earth and produce a spectacle unlike anything seen in recorded human history. For several weeks, possibly longer, Betelgeuse will be visible in the daytime sky, a second point of light alongside the Sun, bright enough to cast faint shadows at night. It will be the brightest object in the night sky by an enormous margin, outshining the full moon, transforming the familiar shape of Orion beyond recognition. Every human alive at that moment will be able to look up and see with their own eyes a star dying, an event playing out across 700 light-years of space, arriving as light on the retinas of people who will have no way of knowing how long that moment has been traveling toward them. When a star like our Sun reaches the end of its life, it sheds its outer layers and leaves behind its dense, collapsed core, a white dwarf. These extraordinary objects contain roughly the mass of an entire Sun compressed into a sphere slightly smaller than Earth, held up not by nuclear fusion, but by the quantum mechanical pressure of electrons refusing to be squeezed any closer together. And here is one of the universe's quiet paradoxes. The more massive a white dwarf is, the smaller it becomes. Extra mass compresses the object further, making it denser and more compact. The relationship between size and mass works in reverse here in a way that has no parallel in ordinary experience, a gentle reminder that the universe does not always follow the rules we are used to. When a star far more massive than our Sun reaches the end of its life and explodes as a supernova, what remains at the center is one of the most extraordinary objects in the universe, a neutron star. the collapsed core of a dead giant, compressed to a sphere only about 12 miles across, yet containing more mass than our Sun. And these objects spin. Some of them spin with breathtaking speed, rotating hundreds of times every second, their surfaces moving at a significant fraction of the speed of light. The fastest known neutron star rotates 716 times per second, something the mass of the Sun, the size of a city, completing over 700 full rotations every single second. It is almost too strange to hold in the mind. Some neutron stars emit powerful beams of electromagnetic radiation from their magnetic poles, and because those poles are not aligned with the rotational axis, the beam sweeps through space like the beam of a lighthouse as the star spins. When that sweeping beam happens to point toward Earth, we detect a regular rhythmic pulse of radio waves arriving with extraordinary precision. These objects are called pulsars, and when the first one was discovered in 1967, the signal was so regular and so precise that for a brief time the astronomers who found it nicknamed it LGM-1, Little Green Men, because the regularity seemed almost artificial. Nature had produced a clock more accurate than any built by human hands. Jocelyn Bell Burnell was a 24-year-old graduate student when she noticed an unusual repeating signal in data from a radio telescope she had helped build at Cambridge University. The signal was so strange and so regular that she and her supervisor initially considered the possibility that it was artificial in origin. It was not. It was the first pulsar ever detected, a rapidly rotating neutron star about 230 light-years away. The discovery was one of the most significant in 20th century astronomy. The Nobel Prize for the discovery was awarded to her supervisor and another colleague. Jocelyn Bell Burnell did not receive it, a decision that generated considerable controversy then and has never quite been forgotten. She has since become one of the most respected astronomers in the world. A white dwarf, when it first forms, shines with intense heat, the residual thermal energy of a star's lifetime compressed into a small, dense sphere. But white dwarfs have no fuel left to burn. They cannot generate new energy. So they cool, slowly and steadily, radiating their stored heat into space over billions of years, gradually dimming from brilliant white to yellow to orange to red. Eventually, in theory, they will cool completely, becoming cold, dark objects called black dwarfs, invisible against the darkness of space. No nuclear reactions, no light, just cold, dense matter drifting silently through the universe. A star's long, quiet final chapter, written in cooling degrees across unimaginable spans of time. Here is a remarkable fact about the age of the universe. It is not old enough yet for a single black dwarf to exist. The cooling process that transforms a white dwarf into a black dwarf takes longer than the current age of the universe. The oldest white dwarfs in existence have been cooling for nearly 13 billion years and are still glowing, faintly, at temperatures of several thousand degrees. The black dwarfs that will eventually populate the far future universe have not yet come into being. They are waiting, in a sense, for time to catch up with them. Objects that are theoretically inevitable, but whose moment has simply not yet arrived. At the far end of the stellar mass scale, beyond the ordinary stars and the giants and the supergiants, lie the hypergiants, rare, extraordinary stars that can contain more than 100 times the mass of our Sun. These objects are so massive that they push against the physical limits of what a star can be. Gravity pulling inward and the pressure of their own radiation pushing outward are nearly perfectly matched, making them structurally unstable, prone to shedding enormous amounts of mass in powerful stellar winds. The most massive known stars, objects like R13601, may contain 200 or more solar masses, so luminous that they emit millions of times more light than our Sun from a single blazing point in the sky. For decades, scientists believed that supernovae were responsible for creating all the heavy elements in the universe. And supernovae do produce many of them. Elements like iron, nickel, and zinc are forged in the final moments of a massive star's life. But gold, platinum, and many of the heaviest metals require something even more extreme. In 2017, astronomers detected both gravitational waves and light from the collision of two neutron stars, an event called a kilonova, and confirmed that this cataclysmic merger was producing gold and platinum in quantities almost beyond imagining. The gold in your jewelry, the platinum in a wedding ring was not born in an exploding star but in the collision of two dead stars compressed to impossible densities, finally meeting after billions of years apart. The most massive stars burn with an intensity that is, in the most literal sense, unsustainable. Where our sun will shine steadily for 10 billion years, a star of 50 or 100 solar masses may exhaust its fuel in just a few million years, a cosmic eye blink. They are brilliant and brief, living at a pace that makes everything around them seem slow. They are born in stellar nurseries, burn with extraordinary luminosity, and die in spectacular supernova explosions, all within a time frame that a smaller, quieter star would consider a brief morning. There is a certain poetry in their brevity. The brightest lights in the universe are also the most fleeting, as if the cosmos could not sustain that much brilliance for long. Our sun is unusual in one quiet way. It travels alone. Most stars in the Milky Way exist not as solitary points of light but as pairs, two stars bound together by gravity and orbiting a common center of mass in a slow, perpetual dance. Some binary stars are widely separated, orbiting each other at distances of many light years, their partnership visible only through careful observation over decades. Others orbit so closely that a year passes in days or hours. Some are mismatched pairs, a large blue giant paired with a small red dwarf, an unlikely coupling maintained for billions of years by the patient persistence of gravity. The universe, it turns out, tends toward companionship. Single stars like our sun are the exception, not the rule. In the closest binary systems, two stars can orbit each other so tightly, separated by less than the distance between Earth and the Sun, sometimes far less, that their outer atmospheric layers overlap and merge. These are called contact binaries, and they present one of the stranger sights in stellar astronomy. Two stars so near each other that material flows between them, exchanged through a shared envelope of gas that connects them like an hourglass. Over time, mass transfers from one star to the other, altering their sizes, their temperatures, their evolutionary paths. They are no longer entirely separate objects, but something in between. Two stars becoming, gradually and inexorably, one. Some stars do not shine with constant brightness. They brighten and dim over regular cycles, pulsing with a rhythm as reliable as a heartbeat. These are called variable stars, and they come in many varieties. Some pulsing because they physically expand and contract, their outer layers oscillating over days or weeks. Others vary because a companion star periodically passes in front of them from our perspective, briefly dimming the light we receive. One particular class of variable star, the Cepheid variables, pulse with a period directly related to their intrinsic brightness, a relationship so reliable that astronomers use them as cosmic rulers to measure distances across the galaxy and beyond. They are the universe's metronomes, keeping time across thousands of light years. You are made of stardust, this much is widely known, but the story is more specific and more extraordinary than that phrase suggests. The oxygen you breathe was forged in the cores of stars that lived and died before our sun was born. The calcium in your bones was created in a supernova explosion. The iron in your blood was assembled in the final moments of a massive star's life. And the gold in any piece of jewelry you own, the silver, the uranium, the heaviest elements on Earth, was born in the collision of two neutron stars somewhere in the ancient galaxy, scattered into space, gathered into the cloud that formed our solar system, and eventually concentrated into the ground beneath your feet. You are, in the most literal sense, recycled starlight. Every atom in your body is ancient. The hydrogen atoms, the most common element in your body, were forged in the first few minutes after the Big Bang, 13.8 billion years ago. The heavier elements, the carbon, the nitrogen, the oxygen, the calcium, the phosphorus, were created inside stars that lived out their entire lives and died before our solar system even began to form. Those stars burned, collapsed, exploded, and scattered their contents into the interstellar medium. That enriched material drifted through space for millions of years until gravity gathered it into the cloud from which the Sun and Earth eventually condensed. You are not just connected to the stars. You are built from them, assembled from the ash of ancient fires, temporarily organized into something that breathes and wonders and looks up at the sky. It is one of the most quoted comparisons in all of astronomy, and it bears repeating in the quiet of this moment. The estimated number of stars in the observable universe, somewhere in the range of a septillion or 10 followed by 24 zeros, exceeds the number of grains of sand on every beach and desert on Earth. Every grain of sand on every shoreline, every dune, every sandbar, all of it combined, and still the stars outnumber them. Each of those stars a sun, many of them larger than ours, most of them ancient, all of them burning in the dark, right now, in every direction, at distances the mind cannot truly hold. And here you are, beneath all of that, breathing softly, growing still. For a while, the number 2 trillion became one of the most quoted figures in popular astronomy. 2 trillion galaxies, each containing hundreds of billions of stars, scattered across the observable universe in every direction. Then, newer data arrived, and the estimate was revised downward. Hundreds of billions, astronomers now suggest, is likely closer to the truth. And yet that revision changes nothing about the essential feeling of the number. Hundreds of billions of galaxies, each one a vast, slowly rotating collection of stars and gas and dark matter and ancient light. Each one a universe in miniature, too large to fully comprehend, too numerous to count, drifting through the dark in every direction as far as our finest instruments can see. Across the hundreds of billions of galaxies in the observable universe, astronomers have identified 3 broad categories of shape. Spiral galaxies, like our own Milky Way, have flat, rotating disks with sweeping arms of stars and gas curling outward from a central bulge, graceful, structured, luminous. Elliptical galaxies are rounder and smoother, ranging from nearly spherical to elongated ovals, filled mostly with older stars and very little gas, their star-forming days largely behind them. And then there are the irregular galaxies, those that fit neither category, their shapes chaotic and asymmetric, often the result of gravitational interactions or collisions with neighboring galaxies. 3 types, and within each type, an infinite variety of individual character. Our galaxy is not a simple spiral, it is a barred spiral, a distinction that refers to an elongated bar of stars running through the galactic center, from which the spiral arms extend outward like the arms of a pinwheel attached to a handle. This bar is made of older stars and stretches roughly 27,000 light-years across the heart of the galaxy. The spiral arms, including the Orion spur where we reside, curve outward from the ends of this bar in long, luminous arcs populated with younger stars, gas clouds, and stellar nurseries. We know all of this not from seeing our galaxy from the outside, which we cannot do, but from painstakingly mapping the positions and motions of billions of individual stars from our vantage point within. Elliptical galaxies are the elder statesmen of the galactic world. Vast, smooth, rounded collections of mostly old stars, their active, star-forming years long past. Unlike the spirals, with their blue-white young stars and luminous gas clouds, elliptical galaxies glow with the warm, reddish-yellow light of ancient suns, stars that formed billions of years ago and have been burning slowly ever since. They contain very little of the raw gas and dust needed to form new stars, their interstellar material either consumed long ago or expelled by the energetic activity of their early years. Some elliptical galaxies are among the largest objects in the universe, giant ellipticals at the centers of galaxy clusters, containing trillions of stars accumulated over billions of years of mergers and collisions. Our Milky Way, with its 100 to 400 billion stars, is a mid-sized galaxy, not small, but not among the giants either. The largest galaxies in the universe are elliptical giants sitting at the centers of massive galaxy clusters, grown enormous through billions of years of consuming smaller galaxies that strayed too close. These giants can contain up to 100 trillion stars, a number so large that if you counted 1 star per second, it would take over 3 million years to reach the total. IC 1101, one of the largest known galaxies, is about 50 times the diameter of the Milky Way and sits at the center of a galaxy cluster a billion light-years away, a quiet, ancient colossus that has been gathering light and mass since the early universe. At the opposite end of the galactic scale from the giants are the dwarf galaxies, small, faint, often irregular collections of stars that populate the outskirts of larger galaxies in great numbers. Some dwarf galaxies contain only a few thousand stars, their total light so dim that they are nearly invisible against the background sky even with powerful telescopes. The Milky Way is surrounded by dozens of these small companions, satellite galaxies orbiting our own in slow, long paths. Some of them are being gradually pulled apart by the Milky Way's gravity, their stars drawn out into long tidal streams that arc across thousands of light years of space. They are being consumed, slowly and gently, absorbed into something larger, their individual identities dissolving over billions of years into the body of our galaxy. Our galaxy forms new stars at a relatively modest pace, perhaps a few solar masses worth of new stars every year, a gentle and sustainable rate of stellar birth. But elsewhere in the universe, there are galaxies undergoing something far more dramatic. Starburst galaxies, often triggered by collisions or close encounters with neighboring galaxies, can form new stars at rates hundreds or even 1,000 times greater than the Milky Way. These galaxies blaze with the blue-white light of millions of young, massive stars forming simultaneously. Their gas clouds compressed by gravitational interactions into dense knots that collapse into stars at an extraordinary pace. They are brief episodes of cosmic extravagance, burning through their available gas in a few 100 million years before settling into a quieter existence. Galaxies are not randomly scattered through space. They are organized into a hierarchy of structures, each level bound together by gravity and nested within the next. Individual galaxies gather into groups of a few dozen, like our own local group. Groups cluster together into galaxy clusters containing hundreds or thousands of galaxies. Clusters in turn are organized into superclusters spanning hundreds of millions of light years, and superclusters are connected to one another by vast filaments of dark matter and gas, forming the cosmic web that defines the large-scale structure of the universe. At every scale, from the smallest galaxy group to the largest supercluster, gravity is the architect, the patient, invisible force drawing things together across unimaginable distances. The largest known structures in the universe are not galaxies or galaxy clusters or even superclusters. They are the filaments, immense threads of dark matter and gas along which galaxies are strung like luminous beads on an invisible wire. These filaments can stretch for billions of light years, connecting clusters and superclusters across the vast expanse of the observable universe. The Hercules Corona Borealis Great Wall, one of the largest known structures, spans roughly 10 billion light-years, a significant fraction of the entire observable universe. At these scales, individual galaxies become invisible, too small to distinguish, and what remains is a pattern, a web of light and dark, structure and void, repeated across the cosmos with a kind of quiet mathematical regularity. When astronomers map the large-scale structure of the universe, plotting the positions of millions of galaxies across billions of light-years, what emerges is one of the most beautiful images in science: a web, a vast, intricate, three-dimensional network of glowing filaments surrounding great dark voids looking remarkably like the structure of a neural network, or the web of a spider, or the branching pattern of blood vessels in a living body. The resemblance is not coincidental in a mystical sense, but it is deeply meaningful in a physical one. These are the natural shapes that emerge when gravity acts on matter distributed across space over billions of years. The universe organizes itself into webs, into networks, into patterns that feel, in some wordless way, familiar. The spaces between the filaments of the cosmic web are not simply empty. They are voids, regions of space that contain far fewer galaxies than the surrounding structure, where matter has been drawn away over billions of years toward the denser filaments and clusters. These voids can span hundreds of millions of light years, vast bubbles of relative emptiness in the fabric of the universe. They are not completely empty. A few galaxies do exist within them, solitary and spread thin. But compared to the bustling density of the filaments and clusters, the voids are places of extraordinary quiet, islands of near-nothingness in a universe that trends everywhere else toward gathering and clustering and drawing together. The scale of cosmic voids is difficult to hold in the mind. The largest of them span hundreds of millions of light years, regions of space so large that if our entire local group of galaxies were placed inside one, it would be like dropping a single grain of sand into an ocean. Light, traveling at 186,282 miles per second, would take hundreds of millions of years to cross from one side to the other. And yet these voids are not featureless. Within them, subtle filaments and walls of faint galaxies can sometimes be detected, like the ghost of a structure that almost formed but was pulled apart before it could fully coalesce. Even the emptiest places in the universe contain echoes of what might have been. The Boötes void is one of the largest known underdense regions in the universe, a roughly spherical expanse of space about 330 million light-years in diameter, located in the direction of the constellation Boötes. When it was discovered in 1981, astronomers were surprised by its size and the relative absence of galaxies within it. Where most regions of that volume would contain thousands of galaxies, the Boötes void contains only a handful, perhaps 60 known galaxies scattered through a space that might be expected to hold thousands. The void is so anomalously large and empty that when it was first reported, one astronomer famously remarked that if the Milky Way had been located in its center, humanity would not have discovered other galaxies until the 1960s. On human timescales, galaxies appear eternal and unchanging, fixed points of light in the night sky, present and permanent. But on cosmic timescales, galaxies are dynamic, restless, constantly interacting with their neighbors through gravity. Collisions and mergers between galaxies are not rare events. They are a fundamental part of how galaxies grow and evolve over billions of years. The Milky Way has already consumed several smaller galaxies in its past, and evidence of those ancient mergers can be found in streams of stars that still arc across the sky, the dispersed remnants of galaxies that fell into ours long ago. These events unfold so slowly, over hundreds of millions of years, that no human generation will ever witness more than a single frozen moment of one. The word collision, when applied to galaxies, is somewhat misleading. When two galaxies pass through each other, the stars within them almost never make direct contact. This is because the distances between individual stars, even within a dense galaxy, are so enormous that two galaxies can interpenetrate almost like ghosts passing through each other, their stars sweeping past one another at vast distances, close enough to have their orbits dramatically altered by gravity, but rarely close enough to actually collide. What does collide, magnificently and violently, is the gas and dust between the stars, compressed by the encounter into dense clouds that collapse into enormous bursts of new star formation, lighting up the merging galaxies with the blue-white brilliance of millions of newborn suns. The universe is 13.8 billion years old, and for the first few 100 million years of its existence, there were no galaxies. Only a dark, cooling fog of hydrogen and helium slowly being drawn by gravity into the first structures. Then, about 400 million years after the Big Bang, the first galaxies flickered into existence. Small, irregular and intensely active, burning through their gas at extraordinary rates. The James Webb Space Telescope has now detected some of these ancient galaxies, their light having traveled for over 13 billion years to reach us. Looking at them is like looking at a photograph of the universe's childhood, small, bright, chaotic objects that would eventually, over billions of years, grow and merge and settle into the grand spirals and ellipticals we see today. Every time we look at a distant galaxy, we are looking into the past. Light travels fast, 186,282 miles per second, but the universe is vast, and the most distant galaxies are so far away that their light takes billions of years to reach us. The galaxy we observe is not the galaxy as it exists now, but as it existed when that light first began its journey. Some of the galaxies we study today no longer exist in the form we observe them. They have merged, evolved, changed beyond recognition in the billions of years since their light left them. We are, in a very real sense, archaeologists of light, reading the ancient history of the universe in the photons that arrive at our telescopes after journeys of unimaginable length. At the centers of some galaxies, particularly in the early universe, there exist objects of almost incomprehensible brightness. Quasars, short for quasi-stellar objects. A quasar is powered by a supermassive black hole actively consuming enormous amounts of material. As gas and dust spiral inward toward the black hole, they form a superheated accretion disk that radiates energy across the electromagnetic spectrum with a luminosity that can outshine the entire galaxy surrounding it by factors of hundreds or thousands. From Earth, early quasars appeared as point-like sources of light, indistinguishable from stars. It took decades of careful observation before their true nature was understood. They are, in essence, the most energetic, sustained phenomena in the universe. A single quasar at its peak brightness can emit more light than an entire galaxy containing hundreds of billions of stars. The energy output of the most luminous quasars is so extreme that it strains the imagination, powered by black holes consuming the equivalent of hundreds of solar masses of material every year, converting a fraction of that mass directly into energy through the physics of accretion. The most luminous quasar known, J0529-4351, shines with the equivalent brightness of 500 trillion suns. One object, 500 trillion suns. A single point of light in the early universe, burning with an intensity that makes everything around it seem dim, its light still crossing the cosmos after billions of years of travel, still bright enough for our telescopes to detect. The universe we live in today is a quieter place than the one that existed billions of years ago. In the early universe, quasars were abundant. The supermassive black holes at the centers of young galaxies were actively feeding on the plentiful gas and dust available in those densely packed, newly forming structures. As the universe expanded and that raw material was gradually consumed or dispersed, the quasars began to quiet down. The black holes at galactic centers did not disappear. They are still there, including the one at the center of our own Milky Way, but most of them are no longer actively feeding at the rates that once made them blaze as quasars. They have settled into a quieter existence, present but patient, waiting in the dark centers of their galaxies. The largest gravitationally bound structures in the universe are galaxy clusters, immense collections of hundreds or thousands of individual galaxies, all held together by their combined gravitational pull and embedded in vast clouds of superheated gas. These clusters take billions of years to assemble, growing through the gradual infall of smaller groups and individual galaxies drawn in from the surrounding cosmic web. Within a cluster, galaxies interact constantly, passing close to one another, distorting each other's shapes, occasionally merging. The overall structure of a cluster is itself dynamic, slowly evolving as new members arrive and the hot intracluster gas radiates energy away into space. They are among the most complex and dramatic environments in the universe, and yet from Earth, they appear as nothing more than faint smudges of light. The nearest large concentration of galaxies beyond our own local group is the Virgo cluster, a sprawling collection of more than 1,300 galaxies located about 65 million light-years from Earth in the direction of the constellation Virgo. It is the gravitational heart of our larger cosmic neighborhood, the Virgo supercluster, and its combined mass is slowly drawing our local group toward it, though that journey will take billions of years to complete. At its center sits M87, a giant elliptical galaxy of extraordinary size and the home of the famous black hole whose image was captured in 2019. The light we see from the Virgo cluster tonight left its galaxies 65 million years ago when dinosaurs still walked the Earth. The space between the galaxies in a cluster is not empty. It is filled with a diffuse but extraordinarily hot gas, the intracluster medium, heated to temperatures of tens of millions of degrees by the gravitational energy of the cluster and the shock waves from ancient galaxy collisions. This gas glows in X-rays, invisible to the naked eye but detectable by space-based X-ray observatories. It contains more mass than all the galaxies in the cluster combined, a vast reservoir of hot plasma threaded through the space between the stars and galaxies, a reminder that the universe between things is rarely truly empty. Even the most desolate-looking spaces contain matter, diffuse, invisible, extraordinarily energetic matter drifting in the dark. Galaxy clusters sit at the top of the hierarchy of gravitationally bound structures, assemblies of matter held together by their own gravity that will remain bound to each other even as the universe continues to expand. Larger structures like superclusters and the cosmic filaments are not truly gravitationally bound in the same way. The expansion of the universe will eventually pull them apart, dispersing their member galaxies into the growing void. But galaxy clusters are dense enough and massive enough that their gravity will hold them together essentially forever, even against the relentless expansion driven by dark energy. In the far future universe, when the last stars have faded and the great voids have grown unimaginably vast, galaxy clusters will remain, the final islands of structure in an otherwise empty cosmos. Step back far enough that entire superclusters become small features in a larger pattern, and the universe reveals one of its most beautiful and unexpected qualities. It looks like a web, a vast three-dimensional network of glowing filaments, each one containing billions of galaxies, connecting at luminous nodes where the greatest clusters of galaxies congregate, surrounding enormous dark voids where almost nothing exists. Scientists call it the cosmic web, and it is the largest pattern in nature, a structure that emerged from the quantum fluctuations of the earliest universe, amplified over 13.8 billion years of gravitational attraction into something of breathtaking intricacy and scale. You are inside it right now. One small warm creature on one small warm planet, woven into the fabric of something almost impossibly large and impossibly beautiful, breathing quietly in the dark. There is a speed limit built into the fabric of the universe, and nothing has ever been observed to exceed it. Light travels at 186,282 miles per second, a number so large it barely registers as a speed at all, more like a property of space itself than a measurement of motion. In 1 second, light could circle the entire Earth 7.5 times. In 8 minutes, it crosses the 93 million miles between the Sun and our planet. In a year, it covers nearly 6 trillion miles. And yet even at this extraordinary pace, the universe is so vast that light takes millions and billions of years to cross the distances between its most remote structures. The speed of light is the fastest thing there is, and it is still nowhere near fast enough to make the universe feel small. The universe has a rule written into its deepest mathematics that nothing possessing mass can ever be accelerated to the speed of light. As an object with mass moves faster, it requires more and more energy to accelerate further, and as it approaches the speed of light, the energy required approaches infinity. There is no amount of force that could push a massive object all the way to that limit. Light itself can travel at that speed because photons, the particles of light, have no mass at all. They are, in a sense, made of pure speed, born moving at 186,282 miles per second and incapable of traveling at any other velocity. The universe sets its boundaries quietly, not with walls, but with mathematics, and the speed of light is perhaps the most fundamental boundary of all. A light year is not a measure of time, though its name suggests otherwise. It is a measure of distance, the distance that light, traveling at 186,282 miles per second without pause, covers in the span of 1 full year. That distance is approximately 5.88 trillion miles. When astronomers say that a star is 100 light years away, they mean that its light has been traveling for 100 years to reach us, that the star we see tonight is the star as it existed a century ago. Light years are the natural unit of cosmic distance, chosen not for convenience but because the universe is simply too large for any smaller unit to be practical. Miles and kilometers become meaningless at these scales, like measuring the distance across a continent in inches. The observable universe, the region of space from which light has had enough time since the Big Bang to reach us, stretches about 93 billion light years from edge to edge. It is important to sit with the word observable here. This is not the entire universe, only the portion we can see. The full universe may be vastly larger. Some models suggest it extends for trillions of light years, or perhaps infinitely. The 93 billion light-year figure is simply the horizon of our visibility, the edge of the cosmic sphere within which any light emitted since the beginning of time could theoretically have reached us. Beyond that horizon, there is almost certainly more galaxies, more stars, more worlds, simply too far away, and the universe too young for their light to have arrived yet. Every observation in astronomy is an observation of the past. The moon we see tonight is the moon as it was about 1.3 seconds ago. The sun is the sun as it was 8 minutes ago. The nearest star beyond our sun appears as it was 4 years ago. Distant galaxies appear as they were millions or billions of years ago. There is no way to see the universe as it is right now. The delay imposed by the finite speed of light is absolute and unavoidable. In a profound sense, astronomers are historians as much as scientists, reading the universe's past in the light that has taken eons to arrive. The night sky is not a window onto the present. It is an archive, luminous and ancient, of everything that has ever shone. The warmth you feel from sunlight on a clear afternoon, that gentle, familiar heat pressing against your skin, departed the surface of the sun approximately 8 minutes and 20 seconds before it arrived. It spent those 8 minutes crossing 93 million miles of empty space, encountering nothing, traveling in an absolutely straight line at the speed of light, until it met the atmosphere of a small blue planet and found its way through billions of air molecules to the surface of your skin. That warmth is not happening now in any simple sense. It is the echo of something that occurred 8 minutes ago, on a surface 93 million miles away, arriving precisely on time, as it always does, with the quiet reliability of a star that has never once failed to rise. On a clear, dark night, if you know where to look, you can find a faint, soft smudge of light in the constellation Andromeda. That smudge is an entire galaxy, a trillion stars, a structure 200,000 light years across, and the light reaching your eyes from it tonight has been traveling for 2.5 million years. It left Andromeda when our ancestors were early hominins, walking the African savanna with stone tools and no knowledge of what lay above them in the night sky. That ancient light crossed the intergalactic void for 2.5 million years, through absolute darkness and absolute cold, until it entered Earth's atmosphere and focused itself through the lens of your eye onto the retina at the back of your skull. You are receiving a 2.5 million year old message tonight, simply by looking up. Beyond the most distant galaxies, beyond the most ancient quasars, there is a boundary in space and time beyond which we cannot see, not because our telescopes are not powerful enough, but because the early universe was opaque. For the first 380,000 years after the Big Bang, the universe was filled with a dense, hot plasma through which light could not travel freely. The cosmic microwave background is the light released at the moment that plasma cooled enough to become transparent. A flash of radiation emitted everywhere simultaneously, 13.8 billion years ago, that has been traveling ever since. It fills the entire sky in every direction, a faint whisper of microwave radiation that represents the absolute limit of our cosmic vision, the oldest light in the universe, still arriving after all this time. The photons that make up the cosmic microwave background have been in motion for 13.8 billion years, the entire age of the universe. They were born in the first great moment of cosmic transparency, when the universe cooled enough for atoms to form and light to flow freely for the first time. Since that moment, they have been traveling outward in every direction through an expanding universe, their wavelengths stretched by that expansion from the short wavelengths of visible light into the much longer wavelengths of microwaves. The universe has stretched those photons like taffy over 13.8 billion years of expansion, cooling them from thousands of degrees to just 2.7 degrees above absolute zero. They are the oldest travelers in existence, and they pass through you right now as you lie still, every moment of every day. One of the most extraordinary predictions of Einstein's general theory of relativity, confirmed repeatedly by experiment, is that time does not pass at the same rate everywhere. In regions of strong gravity, time runs more slowly than it does in regions of weaker gravity. A clock placed near a massive object will tick more slowly than an identical clock placed far from that object. This is not a malfunction of the clock, not an illusion or a measurement error. It is a real physical effect, a genuine difference in the rate at which time passes. The stronger the gravitational field, the more pronounced the effect. Near the event horizon of a black hole, the slowing becomes extreme. Even on Earth, clocks at sea level tick very slightly more slowly than clocks on mountaintops, where gravity is marginally weaker. Einstein's special theory of relativity reveals another form of time dilation, one that depends not on gravity but on velocity. The faster an object moves, the more slowly time passes for it relative to a stationary observer. This effect is negligible at ordinary speeds, but becomes significant as velocities approach the speed of light. A hypothetical traveler moving at 99% of the speed of light would experience time passing far more slowly than someone who remained stationary, aging only a fraction as fast, experiencing only a fraction of the time. It is one of the universe's most counterintuitive properties. That motion and gravity both reach into the fabric of time and slow it, gently or dramatically, depending on their intensity. Time is not a fixed and universal current. It bends. The effects of time dilation are not confined to thought experiments and hypothetical near-light speed travel. They are measurable right now in our own world in the bodies of astronauts orbiting the Earth aboard the International Space Station. Moving at about 17,500 miles per hour and sitting slightly further from Earth's gravitational center, astronauts experience two competing time dilation effects. Their speed slows their time slightly, while the reduced gravity speeds it up slightly. The net result is that they age just fractionally more slowly than people on the ground, a difference of only a few milliseconds over a 6-month mission, but a real and measurable difference nonetheless. Time dilation is not a theory confined to textbooks. It is happening right now to human beings orbiting above our heads. The actual accumulated time difference experienced by astronauts on the International Space Station over a typical 6-month mission is on the order of a few milliseconds, an almost imperceptibly small amount by everyday standards, but significant enough that the GPS satellites orbiting Earth must have their atomic clocks adjusted to account for relativistic effects, or the positioning data they provide would drift into uselessness within hours. The mathematics of Einstein's relativity is not abstract or academic. It is built into the infrastructure of modern life, accounted for in every GPS calculation made by every device that asks where it is in the world. Relativity is not a theory we merely believe. It is a fact we rely on every single day without thinking about it. Near the event horizon of a black hole where gravity is so intense that even light cannot escape, the slowing of time becomes extreme. An astronaut orbiting just outside the event horizon of a sufficiently massive black hole would experience time passing far more slowly than an observer watching from a safe distance. Hours near the event horizon might correspond to years or centuries passing for the distant observer. This is not science fiction. It is a direct prediction of general relativity, confirmed in its less extreme forms by many experiments. The universe near a black hole is a place where time loses its familiar shape entirely, where the distance between moments stretches like the space between stars, vast and quiet and almost beyond imagining. Light is one of the universe's great paradoxes. In some experiments, it behaves unmistakably like a wave, spreading out, interfering with itself, diffracting around corners, producing the patterns of alternating brightness and darkness that are the hallmark of wave behavior. In other experiments, it behaves unmistakably like a particle, arriving in discrete, indivisible packets of energy, interacting with matter one quantum at a time, leaving the kind of precise, localized marks that waves never do. It is both, and it is neither, a thing that transcends the categories our minds have built to organize experience. This wave-particle duality is one of the foundational strangeness of quantum mechanics, a property not just of light, but of all matter at the subatomic scale, a reminder that reality at its smallest scales does not work the way we expect. The individual packets of light, the particles aspect of light's dual nature, are called photons. They are remarkable objects. They carry no mass, which is why they can travel at the speed of light. They carry energy, which they deliver when they are absorbed by matter, warming your skin in sunlight, triggering the chemical reactions in your eyes that allow you to see, driving photosynthesis in the leaves of plants. Each photon carries a specific amount of energy determined by its frequency. The higher the frequency, the more energetic the photon. A gamma-ray photon carries vastly more energy than a radio wave photon, even though both travel at the same speed. Photons are the universe's messengers, massless, swift, and ancient, carrying information across cosmic distances at the only speed the universe allows. Visible light is just one small part of a vast family of electromagnetic radiation, a spectrum that includes radio waves at one end with wavelengths stretching to kilometers in length, and gamma rays at the other end with wavelengths smaller than an atomic nucleus. Microwaves, infrared, ultraviolet, X-rays, all of them are electromagnetic radiation, all of them are made of photons, and all of them travel at exactly the same speed, 186,282 miles per second. The difference between a radio wave and a gamma ray is simply the energy and frequency of their photons. nothing more. The entire electromagnetic spectrum, from the longest wavelength to the shortest, is one continuous family of phenomena, different notes of the same fundamental song, all traveling at the same extraordinary speed. Of the entire electromagnetic spectrum, spanning wavelengths from kilometers to fractions of an atomic nucleus, the human eye can detect only a tiny window, a narrow range of wavelengths roughly between 380 and 700 nanometers. We call this visible light, but the name is parochial. It is visible only to us, only to eyes that evolved under particular conditions on a particular planet. Everything outside that narrow window, the radio signals filling the air around us, the infrared heat radiating from our own bodies, the ultraviolet light burning invisibly above a summer beach, the X-rays passing through our flesh at the doctor's office, all of it is invisible to us, present and real, and filling the universe in every direction, beyond the reach of the only sense we have developed to see. Everything visible to the naked human eye, every star, every planet, every cloud and mountain and ocean and face, represents a vanishingly small fraction of what actually exists. Infrared radiation surrounds us constantly, radiated by every warm object. Radio waves from distant galaxies pass through our bodies every moment. Neutrinos from the sun, 100 trillion of them every second, stream through your body right now without interacting with a single atom of your flesh. Dark matter, which constitutes 27% of the universe's total mass energy, passes through everything without leaving a trace we can directly detect. The universe is almost entirely made of things we cannot see, hear, or feel. What we perceive directly is the thinnest possible surface of a reality that extends in directions we have only begun to map, almost infinitely deeper. Radio waves are the longest wavelength form of electromagnetic radiation, and the universe produces them in abundance. Pulsars sweep regular beams of radio waves across the cosmos. Distant galaxies emit radio radiation from their active cores. The cosmic microwave background fills the entire sky with microwave radiation, the long wavelength cousin of visible light. Cold hydrogen gas, the most common substance in the universe, radiates at a specific radio wavelength of 21 centimeters, a signal so consistent and so universal that it has been proposed as a potential frequency for communication with other civilizations, if they exist, a wavelength known to any intelligence that has discovered the physics of hydrogen. Radio waves from space carry information from the most distant and ancient structures in the universe, arriving silently at our antennae after journeys of billions of years. One of the great advantages of radio astronomy is that the universe is largely transparent to radio waves. They pass through clouds of gas and dust that block visible light completely. Many of the most interesting regions of the galaxy, the dense stellar nurseries, the galactic center, the regions of active star formation, are hidden behind thick clouds of dust that are impenetrable to optical telescopes. But radio waves pass through that dust as if it were not there, carrying information from behind the veil to our antennas on the ground. Radio astronomy has allowed us to map regions of the galaxy that optical telescopes could never reach, to see the structure of the Milky Way from the inside, to detect pulsars, quasars, and the cosmic microwave background, to hear, in a sense, what we cannot see. Infrared radiation, sometimes called heat radiation, occupies the portion of the electromagnetic spectrum just beyond the red end of visible light. Every warm object emits infrared radiation, including your own body. In astronomy, infrared telescopes have proven transformative because infrared light can penetrate the thick clouds of dust that obscure so much of the universe from visible light observation. The James Webb Space Telescope, launched in 2021 and operating primarily in infrared, has used this capability to peer through the dust veils of distant galaxies and stellar nurseries, revealing the hidden structures within with extraordinary clarity. It has also allowed astronomers to see the most distant and ancient galaxies in the universe, objects so far away and so red-shifted that their light has been stretched from visible wavelengths into infrared by the expansion of the universe. Just beyond the blue end of visible light lies ultraviolet radiation, higher energy, shorter wavelength, and largely blocked by Earth's atmosphere before it can reach the surface. The ozone layer in the stratosphere absorbs most of the ultraviolet light coming from the sun, protecting life below from the cellular damage that high doses of UV radiation would cause. This shielding is one of the reasons complex life has been able to flourish on Earth's surface. Some ultraviolet light does reach the ground, enough to cause sunburn on a summer afternoon, but the atmosphere filters out the most damaging wavelengths with quiet efficiency. From space, Earth glows in ultraviolet, a brightness invisible to us from the surface, a reminder of how much the atmosphere between us and the sky is quietly doing on our behalf. At the high-energy end of the electromagnetic spectrum, beyond ultraviolet, lie X-rays and gamma rays, radiation of such short wavelength and high energy that it can penetrate most matter and cause significant damage to living tissue. In the universe, these forms of radiation are produced by the most violent and extreme phenomena: the superheated gas around black holes, the surfaces of neutron stars, supernova explosions, gamma-ray bursts. Earth's atmosphere absorbs X-rays and gamma rays almost completely, which protects us, but also means we need space-based observatories to detect them. When X-ray and gamma-ray telescopes look out at the universe, they see a completely different sky from the one visible at night, a sky blazing with the light of extreme events, a universe in constant violent motion, invisible from the ground, extraordinary from above. Every wavelength of electromagnetic radiation is a different language, and the universe speaks all of them simultaneously. Radio waves tell us about cold hydrogen gas, pulsars, and the large-scale structure of galaxies. Infrared reveals the warmth of forming stars and the shapes of dust clouds. Visible light shows us the surfaces of stars and the colors of nebulae. Ultraviolet traces the hottest young stars and the structure of distant galaxies. X-rays map the superheated gas in galaxy clusters and the furious activity around black holes. Gamma rays mark the most explosive events in the cosmos. To understand the universe fully, we must learn to read all of these languages, to listen to all of its voices at once, to let the full electromagnetic chorus wash over us and reveal, frequency by frequency, the true and extraordinary nature of everything that exists. Everything you have ever seen, touched, tasted, or held in your hands, every mountain and ocean and living creature and distant star is made of ordinary matter: protons, neutrons, electrons assembled into atoms, assembled into molecules, assembled into everything we have ever known or named or loved. And all of that, every last particle of it, accounts for approximately 5% of the total content of the universe. 5%. The remaining 95% is something else entirely. Something we cannot see, cannot touch, cannot directly detect with any instrument yet devised. We live in a universe whose dominant constituents are completely invisible to us, like fish who have mapped the currents of a vast ocean but have never once seen the water itself. Just over a quarter of the universe, approximately 27%, is made of something physicists call dark matter. Not dark in the poetic sense of mysterious or foreboding, though it is certainly mysterious, but dark in the literal sense of emitting no light, reflecting no light, absorbing no light. It does not interact with electromagnetic radiation of any kind. It passes through ordinary matter almost without effect. It has never been directly detected in a laboratory, and yet it is everywhere, woven through galaxies and galaxy clusters and the vast cosmic filaments, present in enormous quantities, shaping the universe through its gravitational influence in ways that are unmistakable and unavoidable. It is the dominant form of matter in the universe, far more abundant than the ordinary matter from which everything we can see is made. The single largest component of the universe, comprising roughly 68% of its total mass energy content, is something called dark energy, not a substance in any familiar sense, not particles, not radiation, not anything that can be collected or measured directly. Dark energy appears to be a property of space itself, an energy inherent in the vacuum, present in every cubic centimeter of space throughout the universe. Its primary observable effect is to cause the expansion of the universe to accelerate, to push galaxies apart from one another at an ever-increasing rate. We know it exists because of what it does. What it actually is remains one of the deepest and most unsettling open questions in all of physics. The universe is mostly made of something we do not understand. The reason dark matter has no name more specific than dark is that we genuinely do not know what it is. What we know is what it does not do. It does not emit light of any wavelength. No radio waves, no infrared, no visible light, no X-rays. It does not absorb light passing through it. Beams of electromagnetic radiation pass through regions dense with dark matter without being attenuated. It does not reflect light. There is nothing to bounce back from. In every electromagnetic sense, dark matter simply does not exist. And yet gravitationally, it is profoundly present. It bends the light of distant galaxies as that light passes through it. It shapes the rotation of galaxies. It forms the scaffolding of the cosmic web. Something is there. We simply have no way of seeing it directly. The evidence for dark matter's existence is not theoretical. It is written into the observable behavior of the universe in multiple independent ways, each one pointing to the same conclusion. Galaxies rotate in ways that cannot be explained by the gravity of their visible stars alone. Light from distant galaxies is bent by invisible mass between us and them, an effect called gravitational lensing, revealing the presence of matter that emits no light. The large-scale structure of the cosmic web, the filaments and clusters and voids, could not have formed in the time available without the gravitational contribution of dark matter providing the initial scaffolding. 3 separate lines of evidence from 3 completely different observational techniques, all converging on the same unseen presence. Something is there. The universe is telling us so, in every direction we look. In the 1970s, astronomer Vera Rubin made careful measurements of how stars in spiral galaxies orbit their galactic centers, expecting to find that stars further from the center would orbit more slowly, just as the outer planets in our solar system orbit the Sun more slowly than the inner ones. Instead, she found that stars at the outer edges of galaxies orbit at roughly the same speed as stars near the center, as if there were far more mass distributed throughout the galaxy than the visible stars could account for. This flat rotation curve, as it became known, was one of the most compelling early pieces of evidence for dark matter. Invisible mass distributed in a vast halo around each galaxy, extending far beyond its visible edge, providing the extra gravity needed to keep the outer stars in their unexpectedly swift orbits. Dark matter does not merely coexist with ordinary matter, it structures it. In the early universe, dark matter began clumping under its own gravity before ordinary matter could, forming invisible halos and filaments that became the gravitational framework into which ordinary matter subsequently fell. Galaxies did not form and then accumulate dark matter around them. The dark matter scaffolding came first, and galaxies formed within it. Every galaxy we observe is embedded in a vast halo of dark matter extending far beyond its visible edge, a ghostly cocoon of invisible mass that defines the galaxy's true gravitational extent. Without that scaffolding, galaxies as we know them could not exist. The visible universe is, in a very real sense, built on a foundation we cannot see. Decades of theoretical work and experimental searching have produced many candidate explanations for dark matter, weakly interacting massive particles, axions, sterile neutrinos, primordial black holes, but no candidate has yet been confirmed. Experiments deep underground, shielded from cosmic rays, have searched for the signal of a dark matter particle colliding with ordinary matter and have found nothing. Particle accelerators have looked for evidence of dark matter production in high-energy collisions and have found nothing. Astronomical observations have constrained the possible properties of dark matter particles with increasing precision, ruling out large regions of theoretical possibility, and yet the answer remains elusive. Dark matter is one of the most thoroughly studied mysteries in physics, and after decades of searching, we are still, in the most fundamental sense, completely in the dark. It is worth pausing to appreciate what it means that 27% of the universe is made of something completely unknown. Not poorly understood, unknown. We have no confirmed detection, no laboratory sample, no direct image, no agreed theory. We know dark matter exists with high confidence because its gravitational effects are overwhelming and consistent, but we do not know what it is, where it came from, whether it has internal structure, whether it interacts with itself, or whether it will ever be possible to detect it directly. It is the dominant form of matter in the universe, and it remains entirely outside our understanding. The universe is not hiding it from us deliberately. It is simply made of something our senses and our instruments were not built to perceive. We are looking for something we do not know how to find. If dark matter is mysterious, dark energy is something beyond mystery. It is a profound conceptual challenge to our most fundamental ideas about the nature of space and energy and reality. At least dark matter behaves like matter in the one way that matters most. It gravitates, it clumps, it responds to the presence of other mass. Dark energy does none of these things. It is spread perfectly uniformly throughout space. It does not clump or cluster. It does not respond to gravity in the ordinary way. Instead, it appears to generate a kind of anti-gravity, a pressure that pushes space apart rather than drawing it together. It is the dominant component of the universe, and it is unlike anything in our experience, unlike anything in our theories, a thing we have named and quantified without understanding it at all. The universe has been expanding since the Big Bang. This much has been known since the work of Edwin Hubble in the 1920s. What was not known until 1998 was that the expansion is not slowing down, as gravity would be expected to cause, but speeding up. Distant galaxies are receding from us not just rapidly, but increasingly rapidly. The further away they are, the faster they are moving away, and that motion is accelerating over time. Something is driving this acceleration, pushing space apart against the decelerating influence of gravity, and that something is what physicists call dark energy. Its discovery upended cosmology and forced a fundamental revision of our picture of the universe's ultimate fate. The universe is not gently coasting to a stop. It is accelerating toward a future of ever greater separation and ever deepening cold. In the early universe, the expansion of space was slowing. The enormous mass of matter and radiation in the young cosmos exerted gravitational attraction that acted as a brake on the outward expansion. For several billion years, this deceleration continued. Then, approximately 5 billion years ago, something changed. The density of matter had thinned enough as the universe expanded that dark energy, always present, always pushing, began to win the tug of war against gravity. The expansion stopped decelerating and began to accelerate. Space started expanding faster, year by year, billion by year. The universe we live in now is expanding more rapidly than at any point in its history since the very earliest moments after the Big Bang, and the rate is still increasing. In 1998, two independent teams of astronomers, one led by Saul Perlmutter, the other by Brian Schmidt and Adam Rees, were studying the brightness of Type I supernovae in distant galaxies, using these standardizable stellar explosions as cosmic measuring rods to map the expansion history of the universe. Both teams expected to find that the expansion was slowing. Both teams found the opposite. The distant supernovae were fainter than expected, which meant they were further away than expected, which meant the universe had expanded faster in recent cosmic history than in the more distant past. The discovery was so unexpected, so contrary to prevailing assumptions, that both teams initially suspected error. There was no error. The universe is accelerating, dark energy is real, and in 2011, Perlmutter, Schmidt, and Rees shared the Nobel Prize in Physics for one of the most surprising discoveries in the history of science. The leading theoretical interpretation of dark energy identifies it with something Einstein called the cosmological constant, a term he introduced into his equations of general relativity and later famously described as his greatest blunder before its eventual vindication. The cosmological constant represents an energy density inherent in empty space itself, not a substance filling space, but a property of space as fundamental as its geometry. Every cubic centimeter of space, whether inside a galaxy or in the deepest void, contains the same density of dark energy. It cannot be concentrated or diluted. It cannot be shielded or blocked. It is simply there, woven into the fabric of existence, in every place and at every moment, the most pervasive and most mysterious component of the universe we inhabit. Here is one of the most quietly extraordinary implications of dark energy as a property of space. As the universe expands and creates more space, the total amount of dark energy in the universe increases. Unlike ordinary matter, which thins out as the volume it occupies grows, dark energy maintains a constant density per unit volume. More space means more dark energy, which drives more expansion, which creates more space, which generates more dark energy. It is not a runaway process in the short term. The acceleration is gradual, but over cosmological timescales, this self-reinforcing relationship between space and dark energy will transform the universe into something almost unrecognizable. Galaxies will recede beyond our observable horizon. The cosmic web will unravel. The universe will grow colder and emptier and more vast, and dark energy will fill every increment of that growing vastness with its quiet, inexorable presence. A black hole is not a hole in the ordinary sense, and it is not empty. It is a region of space where matter has been compressed to such extraordinary density that the gravitational field it generates becomes, beyond a certain boundary, inescapable. Not merely difficult to escape, inescapable in the most absolute mathematical sense. The escape velocity, the speed required to break free from the gravitational pull, exceeds the speed of light. And since nothing in the universe can travel faster than light, nothing that crosses that boundary can ever return. Not matter, not energy, not information, not light itself. A black hole is a place from which there is no coming back, a region of space-time that has, in a sense, withdrawn from the rest of the universe entirely, taking with it everything it has ever consumed. The event horizon is one of the most extraordinary concepts in all of physics. A boundary in space that has no physical surface, no wall, no barrier you could touch or see or feel as you crossed it, and yet represents an absolute and permanent point of no return. Cross the event horizon of a black hole, and you have left the observable universe forever. No signal you send outward can ever escape to reach anyone beyond that boundary. No light you emit can travel fast enough to climb out of the gravitational well. From outside, you would appear to freeze at the horizon, your image redshifting into invisibility as time dilation becomes infinite. From inside, you would simply continue falling, perhaps unaware in the first moments that you had crossed the most significant threshold in the universe. General relativity predicts, and observation confirms, that time runs more slowly in stronger gravitational fields. Near the event horizon of a black hole, this effect becomes extreme. An astronaut falling toward a black hole would, from the perspective of a distant observer, appear to slow as they approached the horizon, their movements becoming more languid, their signals arriving more and more redshifted, the frequency of their transmissions dropping towards zero. They would appear to freeze at the horizon, suspended in a moment that never quite concludes, their image fading slowly into a dim, reddened ghost. The astronaut themselves would experience nothing unusual at the moment of crossing. They would fall through the horizon in finite time by their own reckoning. But to the universe outside, they would seem to have stopped at the edge of forever. When a star of sufficient mass, generally more than about 20 times the mass of our Sun, exhausts its nuclear fuel and can no longer support itself against gravity, the core collapses in a fraction of a second. This collapse is so rapid and so complete that not even the quantum mechanical pressure of neutrons can halt it. The core continues collapsing past the neutron star stage, past every known form of resistance, until it compresses to a singularity, a point of infinite density, and a black hole is born. The outer layers of the star, rebounding from the collapsing core, are expelled in a supernova explosion of extraordinary violence. What remains at the center is one of the universe's most extreme objects, compressed from a stellar core into a region of space just a few miles across. Stellar black holes, the kind formed from the collapse of massive stars, are small by cosmic standards. Their event horizons may be only a few miles in diameter. Yet within that tiny sphere of point of no return lies several times the mass of our Sun, compressed to unimaginable density. The Sun itself is 865,000 miles across. A stellar black hole containing 3 solar masses would have an event horizon perhaps 11 miles wide. To put that compression in perspective, if Earth were compressed to black hole density, it would be the size of a marble. The mass would be unchanged. All of it, every gram, every mountain and ocean and atmosphere, compressed into a sphere less than an inch across. Gravity, taken to its logical extreme, is a force of almost incomprehensible thoroughness. Stellar black holes are small and numerous, scattered throughout galaxies wherever massive stars have died. But at the center of most large galaxies, including our own, there exists something in an entirely different category, a supermassive black hole containing not a few solar masses but millions or billions of them, compressed into a region of space no larger than our solar system. How these objects formed is not fully understood. They may have grown from smaller black holes that merged and fed on surrounding material over billions of years, or they may have formed through other mechanisms in the early universe that left no clear observational trace. What is clear is that they are ubiquitous, present in almost every large galaxy, sitting at its center like an ancient invisible anchor, shaping the dynamics of everything around them. At the very center of the Milky Way, about 26,000 light-years from Earth, sits a supermassive black hole known as Sagittarius A star, pronounced Sagittarius A star. Its presence was inferred for decades from the behavior of stars near the galactic center, which orbit in tight, rapid ellipses around an invisible point of immense gravity. Some of these stars complete a full orbit in just a few years, moving at percentages of the speed of light as they swing around their invisible gravitational anchor. No ordinary object, no cluster of stars, no dense cloud of gas could account for the gravitational influence that drives those orbits. Something of enormous mass, compressed into a very small region, had to be there. Sagittarius A star is that something. 4 million suns, the mass of 4 million stars like our own, each one 333,000 times the mass of Earth, all of it compressed into a region of space roughly the size of the distance between the Sun and Mercury. Sagittarius A star is, by the standards of supermassive black holes, relatively modest. Other galaxies harbor black holes thousands of times more massive. But by any human measure, it is an object of extraordinary magnitude, its gravitational influence felt across thousands of light-years of the galactic center. The stars nearest to it move with frantic speed, their orbits precise and measurable, their behavior a perpetual advertisement for the presence of something vast and dark and impossibly dense at the very heart of our galaxy. While Sagittarius A star is impressive by any human measure, it is a relatively small, supermassive black hole by cosmic standards. Some galaxies harbor central black holes of truly staggering scale, objects containing billions of solar masses, their event horizons spanning distances larger than our entire solar system. The black hole at the center of the galaxy, TON 618, has a mass of approximately 66 billion suns. Its Schwarzschild radius, the radius of its event horizon, is about 1,300 times the distance from Earth to the Sun. Our entire solar system, with all its planets and comets and the vast reaches of the Oort cloud, would fit comfortably inside the event horizon of TON 618 with room to spare. These are the largest discrete objects in the universe, singular points of concentrated gravity, ancient and incomprehensibly massive, sitting in the dark hearts of distant galaxies. For most of the history of black hole physics, these objects were known only through their effects: the orbits of nearby stars, the behavior of infalling gas, the gravitational lensing of background light. Then, on April 10, 2019, the Event Horizon Telescope collaboration released the first direct image of a black hole, a glowing ring of superheated gas surrounding a dark central shadow, the visual signature of light bending around the event horizon of a black hole 55 million light-years away. The image had been assembled from radio telescope data collected simultaneously by observatories spread across the Earth, effectively creating a telescope the size of our planet. The result was a blurred but unmistakable portrait of one of the universe's most extreme objects, a dark circle surrounded by fire, exactly as theory had predicted. The black hole in that first historic image resides at the center of a giant elliptical galaxy called Messier 87, or M87, located in the Virgo cluster about 55 million light-years from Earth. M87 is one of the largest and most massive galaxies known, a vast, rounded elliptical containing trillions of stars, accumulated over billions of years of consuming smaller galaxies. At its center, the supermassive black hole generates a relativistic jet, a beam of plasma and energy shooting outward at nearly the speed of light for thousands of light-years into the surrounding intergalactic space. That jet was first observed in 1918 by astronomer Heber Curtis, long before anyone understood what was producing it. The source of that extraordinary beam was not imaged directly until a century later. The black hole at the center of M87 contains 6.5 billion solar masses, making it roughly 1,600 times more massive than Sagittarius A star at the center of our own galaxy. Its event horizon has a diameter of approximately 38 billion kilometers, about 2.5 times the distance from the Sun to Neptune. The shadow visible in the 2019 image, the dark region at the center of the glowing ring, is actually larger than the event horizon itself because the extreme gravity of the black hole bends the paths of photons near it, creating a shadow region somewhat larger than the event horizon proper. That dark circle in that blurred, historic image represents the edge of the knowable, the boundary beyond which no information has escaped nor ever will. Einstein's general theory of relativity predicted over a century ago that accelerating masses should produce ripples in the fabric of space-time, distortions that propagate outward at the speed of light, compressing and stretching space as they pass. These gravitational waves were thought to be so vanishingly small in amplitude that detecting them would be essentially impossible. Then, in September 2015, the LIGO detectors in the United States registered a signal, a tiny oscillation in the length of their 4-kilometer laser arms, a distortion smaller than 1/10,000th the diameter of a proton, produced by two black holes, each roughly 30 solar masses, spiraling together and merging 1.3 billion light-years away. The universe had spoken in a language no human had ever heard before, and for the first time, we had the instruments to listen. The detection of gravitational waves on September 14, 2015, by the Laser Interferometer Gravitational Wave Observatory, or LIGO, is widely regarded as one of the greatest experimental achievements in the history of physics. The signal lasted only a fraction of a second, a brief chirp in the data that encoded the final moments of two black holes spiraling together after perhaps 1 billion years of orbital decay. The entire event, the merger of two black holes each tens of times the mass of our Sun, released more energy in that fraction of a second than all the stars in the observable universe combined emit in light. And the signal that reached Earth after traveling 1.3 billion light-years moved the mirrors of the LIGO detectors by less than the width of a single proton. It is perhaps the most delicate measurement ever made by human hands. When Einstein published his general theory of relativity in 1915, he predicted that accelerating masses would generate gravitational waves, ripples in space-time propagating at the speed of light. He himself was skeptical that such waves would ever be detected, believing they would be too small to measure. For 100 years, his prediction remained unverified, not because physicists doubted it, but because no instrument existed with the sensitivity required to detect the extraordinarily faint signals that astronomical sources would produce. The 2015 LIGO detection closed that century-long gap, confirming the last major unverified prediction of general relativity and opening an entirely new window on the universe. We had previously observed the cosmos through light. Now we could feel it, through the trembling of space-time itself, arriving as a whisper after a billion-year journey through the dark. Among the most extreme objects in the universe, in a category that includes black holes and neutron stars, magnetars occupy a special place of extraordinary intensity. They are a rare type of neutron star with magnetic fields of almost incomprehensible strength, roughly 1 quadrillion times stronger than Earth's magnetic field and 1,000 times stronger than ordinary neutron stars. These magnetic fields are so powerful that they stress and crack the neutron star's rigid crust, producing starquakes and releasing enormous bursts of X-rays and gamma rays that can be detected from across the galaxy. Magnetars are also among the brightest transient sources of radiation in the universe. A single flare from a magnetar in 2004 was bright enough to partially ionize Earth's upper atmosphere from a distance of 50,000 light-years. The magnetic field of a magnetar is not merely stronger than anything on Earth. It operates in a regime so extreme that it would alter the fundamental behavior of matter in its vicinity. At a distance of 620 miles from a magnetar, the magnetic field would be strong enough to distort the electron clouds of atoms, stretching them into elongated cylinders along the field lines, a process called vacuum birefringence at its most extreme. Your molecules would cease to function as molecules. The chemical bonds that hold your body together would be disrupted at the atomic level. You would not be burned or crushed or torn apart in any familiar sense. you would simply cease to be organized matter. And from halfway to the moon, roughly 120,000 miles, the field would still be strong enough to erase the magnetic strip on a credit card. The most powerful magnetic objects in the universe observe no comfortable middle ground. Most stars in the Milky Way orbit the galactic center in relatively orderly paths, their velocities governed by the overall gravitational field of the galaxy. But some stars have been observed moving at extraordinary speeds, hundreds of kilometers per second, fast enough that they are not merely orbiting the galaxy, but escaping it entirely. These are called hypervelocity stars, and they were first predicted theoretically in 1988 before being discovered observationally in 2005. They travel through the galaxy like bullets, their paths straight and fast and unbound by galactic gravity, carrying them toward the intergalactic void on journeys from which they will never return. They are fugitives from their own galaxy, moving through the Milky Way at speeds that will eventually carry them out into the emptiness between galaxies, alone and traveling fast, forever. The mechanism that produces hypervelocity stars is one of the more dramatic gravitational phenomena known to physics, a process called the Hills mechanism, proposed by astronomer Jack Hills in 1988. When a binary star system, two stars orbiting each other, passes too close to a supermassive black hole, the tidal forces of the black hole can disrupt the binary, capturing one star into a tight orbit around the black hole while flinging the other outward at enormous velocity. The captured star pays for the other's escape with its own freedom, settling into an orbit near the black hole while its former companion rockets away from the galactic center at a speed sufficient to escape the entire galaxy. It is a gravitational slingshot of extraordinary violence, one star sacrificed so another can fly. The fastest hypervelocity stars are moving at speeds well above the escape velocity of the Milky Way, the speed required to break free of the galaxy's gravitational pull entirely. Once they cross the boundary of the galaxy, they will continue outward into intergalactic space, traveling through the vast emptiness between galaxies for billions of years, carrying with them whatever planets or companions they may have, drifting further and further from the galaxy that created and then expelled them. They are, in a sense, the loneliest objects in the universe, stars that once burned at the heart of the Milky Way, swept up in a gravitational encounter of extraordinary violence and sent outward into an emptiness so vast and so silent that no light from home will ever catch them again. 13.8 billion years. It is the number at the foundation of all of modern cosmology, the age of everything, the duration of existence itself as we know it. It was determined through multiple independent lines of evidence. The measured rate of cosmic expansion, the ages of the oldest stars, the temperature and structure of the cosmic microwave background, all of them converging with remarkable consistency on the same answer. There is, it should be noted, a subtle ongoing tension in cosmology. Different methods of measuring the expansion rate of the universe give slightly different answers, a discrepancy called the Hubble tension that physicists are actively working to resolve. For now, 13.8 billion years remains the accepted figure, the best answer humanity has yet produced to one of the oldest questions we have ever asked. How long has all of this been here? The name Big Bang is, in some ways, misleading. It conjures the image of an explosion, a violent eruption of matter outward from a central point into a pre-existing void. But that is not what happened. There was no pre-existing void. There was no central point. Space itself, along with time and energy, and all the matter that would eventually form every star and planet and living thing, came into existence at the Big Bang. And it did not explode outward into anything. It expanded, all of it, simultaneously, every point in space moving away from every other point, the way the surface of a balloon expands as it is inflated. There is no center of the universe, no place where the Big Bang happened, because the Big Bang happened everywhere at once, and everywhere is still expanding from it now. In the very first moments of the universe's existence, a period so brief that it makes any human timescale look eternal, the universe underwent a phase of expansion so rapid it defies ordinary comprehension. Called cosmic inflation, this period lasted for only a tiny fraction of a second, somewhere around 10 to the minus 32 seconds, and during that time the universe expanded by a factor of at least 10 to the power of 26. doubling in size perhaps 90 times or more in rapid succession. A region smaller than a subatomic particle inflated to a size larger than the observable universe today. The smoothness of the cosmic microwave background, the flatness of the universe's geometry, the large-scale homogeneity of structure, all of these features are explained naturally by inflation, a period of extraordinary expansion that set the stage for everything that followed. Cosmic inflation is one of the most profound and strange ideas in modern cosmology. The notion that in its first unimaginably brief moments, the universe underwent a period of exponential expansion driven by a form of energy that has since disappeared, leaving no direct trace except in the large-scale structure of everything that exists. The theory was proposed in the 1980s by physicist Alan Guth as a solution to several puzzling features of the observed universe. Why it looks the same in every direction, why its geometry appears flat, why it contains no magnetic monopoles. Inflation solves all of these problems simultaneously, with elegant economy. The evidence for it is indirect but compelling, written into the fine structure of the cosmic microwave background and the distribution of galaxies across the sky. It is one of the most beautiful and unsettling ideas in science, that the universe we inhabit was shaped in its entirety by an event that lasted less than a trillionth of a second. Before inflation, before the first fraction of a second had elapsed, the region of space that would eventually expand into everything we can observe, every galaxy, every star, every atom in every living body, was compressed into a space smaller than a single atom, smaller than a proton, smaller than a quark. At that scale, the distinction between matter and energy, between space and time, between existence and non-existence, dissolves into a realm governed entirely by quantum mechanics, a regime our current physics cannot fully describe. We do not have a complete theory of what happened at that earliest moment before inflation began. We have equations that work beautifully up to a certain point, and then the mathematics breaks down, and what lies beyond that point remains genuinely, profoundly unknown. The universe began somewhere we cannot yet see. In the universe's earliest hundreds of thousands of years, the conditions were so extreme that matter as we know it could not exist. The temperature was too high for electrons to bind to atomic nuclei. Any atom that tried to form was immediately torn apart by the fierce thermal energy of its surroundings. The universe was a dense, hot plasma, a sea of free electrons and nuclei and photons all interacting constantly, the light scattering in every direction, unable to travel more than a tiny distance before being absorbed and re-emitted. This plasma filled all of space, glowing with an intense brightness that nothing could see through. The universe in its first 380,000 years was luminous and opaque, full of light that could go nowhere, energy that could not escape, brilliance with nowhere to travel. Then, approximately 380,000 years after the Big Bang, the universe crossed a threshold. The temperature had dropped enough, to about 3,000 degrees, that electrons could at last bind stably to atomic nuclei, forming the first neutral atoms. Hydrogen and helium, the two simplest elements, condensed out of the plasma in a process astronomers call recombination, though it was not really a recombination, since the electrons and nuclei had never been combined before. With the free electrons gone, the universe became suddenly, dramatically transparent. Light that had been trapped, scattering endlessly through the plasma, could now travel freely in straight lines across space. The universe that had been brilliantly opaque became, in a cosmically brief transition, the transparent cosmos we inhabit today, vast and dark and clear, the light finally free to go wherever it wished. The light released at the moment of recombination did not simply disappear, it has been traveling ever since, filling all of space, moving in every direction, its wavelengths stretched by the expansion of the universe from the warm reddish glow of a 3,000-degree gas into the cold microwave radiation we detect today. It arrives at our instruments from every direction simultaneously, a perfect isotropic glow filling the entire sky, the afterglow of the universe's first moment of transparency. When astronomers map the cosmic microwave background, they are looking at a snapshot of the universe as it existed 380,000 years after its birth. The oldest image it is possible to obtain, a portrait of the cosmos in its infancy, taken in light that has been traveling toward us for 13.8 billion years. Nothing we can observe with any telescope at any wavelength is older than the cosmic microwave background. It is the absolute horizon of observational astronomy, the boundary beyond which the universe was opaque, and no photon from earlier times can have reached us. Every other source of light we study, the most distant galaxies, the most ancient quasars, the first stars, all of them formed after recombination, all of them younger than this primordial glow. The cosmic microwave background is older than galaxies, older than stars, older than any atom heavier than lithium. It is the oldest thing we can see, a faint, cold, perfect whisper of the moment when the universe first became transparent, when light first flew free, when the darkness we know today was born from a brightness we can barely imagine. The cosmic microwave background, when it was first released 380,000 years after the Big Bang, had a temperature of about 3,000 degrees, warm enough to glow with a reddish light visible to human eyes, had any existed. In the 13.8 billion years since, the expansion of the universe has stretched those photons enormously, reducing their energy and their temperature. Today, the cosmic microwave background fills the sky at a temperature of just 2.725 degrees above absolute zero, colder than the coldest place on Earth, colder than any laboratory refrigerator, cold enough that its radiation falls entirely in the microwave range, invisible and imperceptible to our senses. It is the cooling echo of a much hotter universe, a whisper that has been fading for 13.8 billion years and has not yet gone silent. A reminder that the universe we inhabit is the cooled and darkened remnant of something once brilliantly, uniformly, impossibly bright. The cosmic microwave background is not perfectly uniform. When measured with sufficient precision, it shows tiny temperature fluctuations, variations of about 1 part in 100,000, subtle ripples in the ancient light that encode the earliest density variations in the universe. Where the temperature is very slightly higher, matter was very slightly more concentrated. Where it is very slightly lower, matter was very slightly less dense. These tiny variations, quantum fluctuations from the universe's earliest moments, amplified by inflation to cosmic scales, were the seeds of all structure in the universe. Over billions of years, gravity amplified those density variations, drawing matter together in the denser regions and evacuating the less dense ones, until the cosmic web emerged. The filaments and clusters and voids that define the universe's large-scale architecture today. Everything you have ever seen began as a ripple in the oldest light. After recombination, the universe entered a long dark period. Neutral hydrogen and helium filled space, slowly being drawn by gravity into the slight density enhancements left by inflation. But there were no stars yet, no light sources of any kind. The universe was dark, genuinely, completely dark, for hundreds of millions of years, lit only by the fading glow of the cosmic microwave background, cooling steadily toward the temperature of the void. Then, perhaps 100 million years after the Big Bang, the first concentrations of gas became dense enough and hot enough to ignite nuclear fusion at their cores. The first stars switched on, brilliant, massive, burning intensely in the darkness. After hundreds of millions of years of cosmic night, the universe had light again, and nothing would ever be the same. The first generation of stars, called Population 3 stars by astronomers, though none have yet been directly observed, were radically different from the stars we know today. Formed from a gas cloud containing only hydrogen and helium, with no heavier elements to provide additional cooling mechanisms, they could not fragment into small pieces the way modern molecular clouds do. Instead, they collapsed into enormous objects, perhaps hundreds of times the mass of our Sun, burning with an extraordinary intensity that consumed their fuel in only a few million years. They were the universe's first furnaces, the first objects to fuse hydrogen into helium and helium into carbon, oxygen, neon, and the heavier elements that did not exist before them. They were born into absolute darkness, and when they died, they left the universe forever changed. Not a single star from the first generation survives. The most massive of them lived only a few million years before exploding as supernovae or collapsing directly into black holes, seeding the surrounding gas with the first heavy elements the universe had ever contained. Even the less massive among the first stars, if any formed, would have exhausted their fuel and died long before our solar system was born. The universe we live in today is populated entirely by later generations of stars, each one born from gas enriched by the deaths of its predecessors, each one carrying within it the accumulated elemental legacy of all the stars that came before. The first stars are gone, but their influence is everywhere. In the carbon of our atmosphere, the oxygen in our blood, the iron at the center of our planet. They burned in the dark so that everything else could exist. As the first stars burned and died and seeded the universe with heavy elements, the structures around them were also growing. Dark matter halos, the invisible gravitational scaffolding, were merging and accumulating, drawing ordinary matter into their centers, building the first proto-galaxies from the chaos of the early universe. By about 400 million years after the Big Bang, the first recognizable galaxies had formed. Small, irregular, intensely active structures blazing with the light of massive young stars, crowded with supernovae, rich with the raw energy of formation. The James Webb Space Telescope has now observed some of these earliest galaxies, their ancient light arriving after a journey of more than 13 billion years, telling us something about how the universe organized itself in its earliest chapters. They are small and bright and chaotic, the universe's first attempts at the grand architecture it would eventually achieve. Between the moment of recombination, when the universe first became transparent, and the ignition of the first stars, there was a period of perhaps 100 to 200 million years, during which the universe contained no light sources of any kind. The cosmic microwave background had faded to invisibility. No stars burned, no galaxies gleamed. Clouds of neutral hydrogen drifted through the darkness, slowly condensing under gravity, building the structures that would eventually become the first stars and galaxies, but doing so in complete and total darkness. Astronomers call this period the Cosmic Dark Ages, and it is one of the least understood chapters in the history of the universe, simply because there is nothing to observe from that era. No light was emitted, no signal was sent. The universe spent its first 100 million years in a silence and darkness more complete than anything that has existed since. In the moments after the Big Bang, the universe contained only 3 elements in significant quantities: hydrogen, helium, and trace amounts of lithium. Nothing else. Carbon, which forms the backbone of every organic molecule in every living thing. Oxygen, which fills our atmosphere and our lungs. Iron, at the center of our planet and in our blood. Silicon, in the rocks beneath our feet. None of these existed. The universe had no way to make them without stars, without the crushing pressure and heat of stellar cores, where nuclear fusion assembles heavier nuclei from lighter ones. The first stars created carbon and oxygen and neon and magnesium in their cores, and when those stars died in supernova explosions, they scattered those elements into the surrounding gas, enriching it for the next generation. Element by element, star by star, the universe slowly assembled the chemical vocabulary needed to build worlds and, eventually, life. The universe's chemical evolution is a story told in generations. The first stars made the lightest heavy elements and scattered them in death. The second generation of stars, born from that enriched gas, could make still heavier elements and scattered those in turn. Each successive generation of stars has added to the cosmic inventory, building the periodic table element by element, supernova by supernova, neutron star merger by neutron star merger, until the universe contained the full richness of chemical variety we see today. Our Sun is a 3rd or 4th generation star, born from gas that has been through multiple cycles of stellar birth, nuclear fusion, and spectacular death. The relative abundance of elements in the solar system, the ratios of iron to oxygen, carbon to nitrogen, reflects the entire chemical history of the Milky Way, written into the composition of our star and its planets. You are made of the universe's history. The hydrogen atoms in the water molecules of your body were forged in the Big Bang 13.8 billion years ago. The carbon in your DNA, the oxygen you breathe, the calcium in your bones, the iron carrying oxygen through your bloodstream, all of it was created in the nuclear furnaces of stars that lived and died before our solar system formed 4.6 billion years ago. Those stars burned for millions or billions of years, fused their hydrogen and helium into heavier elements, exploded or shed their outer layers into the surrounding gas, and became part of the interstellar medium from which our Sun and Earth eventually condensed. You are not merely connected to the stars. you are assembled from them. Temporarily organized into something that breathes and wonders and feels, but made atom by atom of the universe's oldest work. Of all the facts in this journey through the cosmos, perhaps none is quieter or more personal than this one. The universe is 13.8 billion years old tonight. It will never be this age again. Tomorrow, it will be older. Next year, older still. The configuration of stars and galaxies and dark matter and light that defines the universe at this precise moment, the particular arrangement of everything that exists, will never occur again. This moment is not a point on a circle, endlessly recurring. It is a point on a line, moving in one direction through a universe that is always changing, always aging, always becoming something it has never been before. You are here for a small portion of that line, a brief, luminous interval in the universe's long story. And right now, in this moment, the universe is exactly as old as it is when you are falling quietly, gently into sleep. The word exoplanet contains within it one of the most quietly revolutionary ideas in the history of science. The idea that planets are not unique to our solar system, not a special feature of our particular star, but a common and perhaps universal phenomenon occurring around stars throughout the galaxy and beyond. For most of human history, we had no way of knowing whether other stars had planets. We could only assume, or hope, or imagine. The night sky was full of stars, and those stars might have been utterly alone, burning in empty space, surrounded by nothing. Or they might have had worlds. We simply did not know. The word exoplanet represents the moment we stopped wondering and started finding. The moment the question became, at last, one that observation could answer. In 1995, Swiss astronomers Michel Mayor and Didier Queloz announced the discovery of 51 Pegasi b, a planet orbiting a sun-like star about 50 light-years away in the constellation Pegasus. It was not the kind of planet anyone had expected to find first. It was a gas giant, similar in mass to Jupiter, but orbiting its star in just 4 days, closer to its sun than Mercury is to ours, its surface temperature a blistering 1000 degrees Celsius. Its existence defied the prevailing theories of planetary formation, which suggested that gas giants could only form in the cold outer regions of a solar system. 51 Pegasi b announced, on the very first confirmed detection of an exoplanet around a sun-like star, that other solar systems would not look like ours, and that the universe had more imagination than our theories. 30 years after the first confirmed detection, the catalogue of known exoplanets has grown beyond 6,000 confirmed worlds, with thousands more candidates waiting to be verified. The pace of discovery has been extraordinary, driven first by the Kepler Space Telescope, which stared at a single patch of sky for years and found thousands of planets transiting their stars, and more recently by the TESS mission and the James Webb Space Telescope, which have extended the search across the entire sky and added the ability to study exoplanet atmospheres in unprecedented detail. 6,000 worlds, each one a unique environment, each one a data point in the growing picture of how common planets are, how varied solar systems can be, and how many places in the universe might, under the right conditions, support something like life. One of the most significant conclusions to emerge from the era of exoplanet discovery is that planets are not rare. Statistical analyses of the Kepler mission data suggest that, on average, every star in the Milky Way has at least one planet orbiting it, and many stars have several. Planets, it turns out, are a natural and nearly inevitable consequence of star formation. When a cloud of gas and dust collapses to form a star, the leftover material naturally settles into a disk around the newborn star, and within that disk, planets form through the gradual accumulation of dust and rock and gas. This process appears to happen around almost every star, regardless of the star's size, age, or composition. The galaxy is full of planets. The question is no longer whether they exist, but what they are like. If most stars have at least one planet and the Milky Way contains between 100 and 400 billion stars, then the number of planets in our galaxy alone reaches into the hundreds of billions at minimum, and likely into the trillions when accounting for the multiple planets many stars host. Trillions of worlds orbiting trillions of stars in a single galaxy among hundreds of billions of galaxies. The implications of that number are almost too large to sit with comfortably. Even if the conditions required for life are extraordinarily rare, even if only one planet in a million develops life, and only one in a million of those develops complex life, the sheer number of worlds makes the universe's potential for life a question of extraordinary scope. We are one world. The galaxy contains trillions. The universe contains more still. In our solar system, the fastest orbit belongs to Mercury, which completes a trip around the Sun in 88 days. But in the wider galaxy, we have found planets that make Mercury look leisurely by comparison. Some hot Jupiters and ultra-short period planets orbit their stars in just a few hours, whipping around at extraordinary speeds, so close to their stellar surface that their years pass in the time it takes a human being to sleep and wake. The planet Kepler 78b, for example, orbits its star in just 8.5 hours, skimming the stellar surface at a distance of less than twice the star's radius. At that distance, its surface temperature exceeds 2000 degrees Celsius, and the tidal forces from its star are gradually pulling it apart. It is a world in the final stages of being consumed, a brief, bright, rapidly orbiting ember in the outer catalogue of the universe's extraordinary variety. Of all the alien worlds discovered so far, HD 189733b offers one of the most vividly hostile environments imaginable. It is a deep blue gas giant orbiting a star about 63 light-years away, and its atmosphere is a place of extraordinary violence. Temperatures on its day side reach nearly 1000 degrees Celsius, hot enough that silicate particles, the material of glass, condense in the upper atmosphere and rain downward. But the winds on HD 189733b reach speeds of 5,400 miles per hour, faster than any wind ever recorded on any world in our solar system, blowing that glass rain not downward but sideways in a screaming horizontal torrent of molten silicate particles. It is a planet that rains glass sideways in hurricane-force winds, a place of such profound hostility that it makes every extreme environment on Earth seem gentle by comparison. When the Kepler Space Telescope discovered a planet orbiting two stars at once, astronomers reached almost instinctively for a cultural reference. Tatooine, the fictional desert world in Star Wars, famous for its twin sunsets. Kepler 16b is a real world, about 200 light-years away, roughly the size of Saturn, orbiting a pair of stars that themselves orbit each other. From the surface of Kepler 16b, or from any hypothetical moon orbiting it, the sky would contain two suns, their relative positions and apparent sizes changing slowly as the planet moves through its orbit. The system is not hospitable to life as we know it, too cold, too gaseous, too complex in its stellar dynamics, but its existence confirmed something wonderful, that the universe is not constrained by our imagination, and that the things science fiction writers dream of, the universe has sometimes already built. Among the most extreme exoplanets yet discovered are the lava worlds and ultra-hot Jupiters, planets orbiting so close to their stars that their surfaces or atmospheres reach temperatures of thousands of degrees. On some of these worlds, iron, the same iron that forms the solid core of our planet, exists as a vapor in the atmosphere, rising from a molten surface, condensing on the night side into iron rain that falls back down. Rock itself evaporates. The boundary between the solid ground and the sky dissolves entirely on these worlds, replaced by a continuous cycle of vaporization and condensation, rock rising as gas and falling as liquid in an atmosphere made of the materials we think of as the most permanent and unyielding substances on Earth. They are worlds that redefine what an atmosphere can be made of. At the other extreme from the lava worlds, some exoplanets may be ocean worlds, covered entirely in water with no continents, no shorelines, no beaches, no mountains rising above the surface. These ocean planets, sometimes called water worlds, would have oceans potentially hundreds of miles deep, far deeper than anything on Earth, where the deepest point in the ocean is just under 7 miles. Under the crushing pressure of those deep oceans, water itself would behave differently, compressed into exotic high-pressure phases, perhaps including forms of ice that exist at temperatures well above the normal boiling point of water on the surface. These are worlds where the ocean is not a feature of the landscape but the entirety of it, where life, if it exists, has never known the feel of dry land or the sight of a coast. Between the rocky terrestrial planets and the gas giants, there exists a class of worlds for which our solar system provides no example: the super-Earths. These are rocky or partially rocky planets larger than Earth but smaller than Neptune, occupying a size range that appears to be one of the most common in the galaxy. We have found hundreds of them. Some may be genuinely Earth-like: rocky surfaces, possible atmospheres, temperatures within the range where water could exist in liquid form. Others may be ocean worlds, or worlds with thick hydrogen atmospheres, or worlds whose surface conditions are entirely unlike anything in our solar system. The term super-Earth refers to size, not necessarily to habitability or similarity to our world. They are simply larger than we are, and they are everywhere. One of the most surprising discoveries of the exoplanet era is the apparent prevalence of a type of planet that does not exist in our solar system: the mini-Neptune. These worlds are larger than super-Earths, but smaller than Neptune, with thick gaseous envelopes surrounding rocky or icy cores, and they appear to be extraordinarily common in the galaxy. The Kepler mission found them in enormous numbers. They represent perhaps the most typical kind of planet in the Milky Way, and yet we have nothing like them in our own solar system, where there is a conspicuous gap in planet sizes between Earth and Neptune. Why our solar system lacks this common planetary type is an open question, one that speaks to the particular and perhaps unusual history of our own planetary neighborhood and to the possibility that our solar system is less typical than we once assumed. Not all planets orbit a star. Some have been ejected from their home systems, flung outward by gravitational interactions with other planets or passing stars, their orbits disrupted beyond recovery, sent on trajectories that carry them out of their solar systems entirely and into the cold darkness between the stars. These rogue planets, also called free-floating planets or orphan planets, drift through interstellar space without any star to warm them, without any solar wind, without any light except the distant collective glow of the galaxy. They are among the loneliest objects imaginable, worlds complete in themselves, perhaps with geology and interior heat, perhaps even with subsurface oceans warmed by radioactive decay, drifting forever through the dark with no sun to rise over their horizons, no seasons, no tides, nothing but the quiet of the interstellar void. Recent gravitational microlensing surveys, observations that detect planets by the way their gravity bends the light of background stars, have suggested that rogue planets may be extraordinarily common. Some estimates suggest that there may be more free-floating planets in the Milky Way than there are stars, that for every star burning in the galaxy there may be one or more worlds drifting in the dark between them, untethered and alone. If those estimates are correct, the total number of rogue planets in the Milky Way could be in the hundreds of billions or more. Worlds without suns spread through the galaxy in numbers that rival the stars themselves, a vast, invisible population of dark and drifting objects, each one a world that was formed in the light and warmth of a young solar system and then, through some gravitational misfortune, lost it forever. In the search for life beyond Earth, one concept has become central: the habitable zone, sometimes called the Goldilocks zone, the region around a star where conditions are neither too hot nor too cold for liquid water to exist on a planet's surface. Not too close to the star where water would boil away into the atmosphere and be lost to space. Not too far where it would freeze permanently into ice. But in the gentle middle distance, the zone where temperatures allow water to rest quietly on the surface in liquid form, where oceans are possible, where the chemistry of life as we know it can occur. Earth occupies the habitable zone of our Sun almost perfectly. We have now identified dozens of planets in the habitable zones of other stars. Worlds at the right distance, potentially the right temperature, waiting in the dark for us to learn more about them. The universe has been expanding since the moment of the Big Bang, and everything we currently observe suggests it will never stop. In the early universe, there was reason to wonder whether the expansion might one day slow, halt, and reverse, whether gravity, acting across cosmic scales, might eventually pull everything back together in a mirror image of the Big Bang, a big crunch that would end the universe as dramatically as it began. But the discovery of dark energy in 1998 changed that picture entirely. With dark energy driving an accelerating expansion, the universe appears destined not to collapse but to continue growing forever, each passing eon carrying galaxies further apart, the cosmic web stretching thinner, the universe becoming larger and colder and quieter with every billion years that passes. It will not end with a crunch. It will continue, vast and dark and expanding, into a future so remote it has no name. The expansion of the universe does not merely carry galaxies apart. It carries them apart at speeds that for the most distant galaxies already exceed the speed of light. Not because anything is moving faster than light through space, but because the space between us and them is itself expanding, adding distance faster than light can cross it. Right now, there are already galaxies whose light will never reach us. They are receding too quickly for their photons to make the journey. As dark energy continues to accelerate the expansion, more and more galaxies will cross that horizon, their light red-shifting into invisibility, their presence becoming forever undetectable. In trillions of years, a civilization in our galaxy would look out at a universe that appeared to contain only the Milky Way and its nearest neighbors, the rest of the cosmos having vanished beyond an ever-expanding horizon of cosmic silence. Stars are born from gas. Cold, dense clouds of hydrogen and helium that collapse under gravity and ignite nuclear fusion at their cores. But that gas is not inexhaustible. With every generation of stars, some of the galaxy's gas is locked away permanently in white dwarfs, neutron stars and black holes, objects that will never return their material to the interstellar medium in a form that can form new stars. Other gas is expelled from galaxies entirely by the energetic activity of supernovae and active galactic nuclei. Slowly, over trillions of years, the supply of star-forming gas will dwindle. New stars will form less and less frequently, the galaxy growing quieter and dimmer with each passing era until the last stellar nurseries are exhausted and the final generation of stars ignites for the last time, burning in a universe that will never make another. 100 trillion years from now, a number so large it contains our entire cosmic history roughly 7,000 times over, the last stars will exhaust their fuel and go dark. The smallest red dwarf stars, those slow and patient fires that burn for trillions of years on the barest trickle of nuclear fuel, will be the final lights in the universe. One by one, over unimaginable spans of time, they will dim, cooling from red to infrared to nothing, their surfaces falling below the temperature of visibility, their light fading below the threshold of detection. The universe will not end dramatically. It will not explode or collapse. It will simply grow dark, the way a fire grows dark when the last of the wood has been consumed, not with violence, but with a slow, quiet, inevitable dimming, until the last ember fades and there is only the dark and the cold and the silence of a universe that has burned itself out. If dark energy is not constant, if it grows stronger over time as some models suggest, then the universe may not simply fade into cold darkness. It may end in something far more dramatic. In the Big Rip scenario, the accelerating expansion of space eventually becomes so powerful that it overwhelms every other force in the universe one by one. First, the large-scale structure of the cosmic web is torn apart, galaxy clusters separating, filaments dissolving. Then individual galaxies are pulled apart, their stars scattered into intergalactic space. Then solar systems, the gravitational bonds between stars and their planets overcome by the expanding fabric of space itself. Then planets, their material flung outward as the space within them expands faster than gravity can hold them together. Then atmospheres, then oceans, then mountains, then rocks, then molecules, then atoms themselves. The electromagnetic forces holding electrons to nuclei finally overcome in the universe's last moments. The final dissolution would happen extraordinarily rapidly, the last structures of matter torn apart in a fraction of a second, the universe ending not in darkness and cold, but in a sudden, total and absolute unraveling of everything that exists. A universe that began in extraordinary compression ends in extraordinary expansion. Space itself the agent of its own conclusion, growing without limit until there is nothing left to separate. Right now, in this very moment, you are closer to the stars than you have ever been, not in distance, but in stillness, in the quiet understanding that you and they are made of the same ancient light, breathing the same cosmic patience into existence. The stars do not rush. They burn for billions of years with the same steady rhythm, the same unwavering presence, night after night across the darkness. And you, lying here tonight, have found something of that same stillness, that same capacity to simply be, without urgency, without effort, held by forces you cannot see but that have never once failed to hold you. The atoms in your body remember being starlight. They carry that memory still, encoded in their very structure, in the way they gather and bond and form the temporary, beautiful arrangement that is you. You are not separate from the universe. You are its stillness made flesh. You are what happens when ancient light learns for a brief and luminous moment to rest. We have now peacefully gone through 201 sleepy facts about our universe. You have traveled tonight from the ground beneath you to the edge of the observable universe. You have visited the hearts of stars and the silences between galaxies. You have stood at the event horizons of black holes and drifted through the ancient light of the cosmic microwave background. You have seen the universe as it was 13.8 billion years ago and glimpsed quietly what it might become in the unimaginable distances of the future. There's nothing left for you to do but rest. Close your eyes, let your breathing slow, and let the weight of everything you have heard settle gently into the background. Sleep well, friend. Good night.